Yesterday in this Python group, you have learned about the datasets developed in geo-harmonizer. You have learned how to run machine learning land cover classification. And today we will speak about the Lucas dataset. You learn how to use Landsat and auxiliary data for machine learning. You have probably spoke about how to run random forest or other Ensemble methods. Whenever you want to do such an exercise, you are supposed to use some training data set. And this is typically the weakest point of the whole exercise, as there are lots of satellite images like Landsat, Sentinel, PlanetScope, etc. There are many frameworks for machine learning models, but typically there is a shortage of good representative training data set. And this session is dedicated to introduce the Lucas. The session will have six parts. Initially, I try to discuss and introduce you to Lucas dataset. Then we will show you how to access such datasets using Python API, the software we have developed in the geo-harmonizer project, and we will run Jupyter notebooks. Then I'll tell you about the Lucas dataset harmonization. Then we will have a use case how to use such a Lucas data for validation, land cover validation or other land product validation. And then in the last two parts, we will discuss a little bit more how to use the Lucas dataset with other products like Corine, how to translate the Lucas legend to Corine, and possibly how to perform some class aggregation to perform some research about the influences of the classification nomenclature on the quality indicators. And finally, possibly I will show you that there is also a QGIS plugin to interactively access the Lucas data. To follow the workshop practically, you would need the ODSE VirtualBox, which I believe you have already set up from yesterday. It's all running. This is the first thing. Then you would need EU map library, which is the same library as you used yesterday. You would need just to update from the repository by running git pull. That's it. And of course, the Jupyter notebooks, which we have presented in the same directory as yesterday. There is a Python training directory, and you would find there's 05_Lucas. But there's a bunch of files, 3 or 4 Jupyter notebooks, some Python scripts, and sample data sets for the Lucas validation. But when we get to this point and through the presentation, I would guide you. I will show you where it is and how to update this. So don't worry, please, at the moment. Okay, so this is what we should do. Briefly, what is Lucas dataset? It's a Eurostat or European Union activity. It stands for Land Use and Coverage Area Frame Survey. Originally, this activity started 2000, where Commission decided that we need some real in situ data sets. And they started with mapping or monitoring in situ the agriculture field. They collected information about crops grown. But then they decided to generalize this task. And since 2006, the Lucas dataset is about generic land cover, and it evolves up to 2018. And the main goal is to provide statistical values for estimation of how European Union land cover and land use is changing. That was the primary goal, to really monitor the changes. So the Lucas is not one of the activity, but it's continuous. It started operationally 2006, and every year it is updated. And there are many of topics that it covers. Later on, I will show you what you can explore. I want to mention that it is to some degree unique ground truth, because people go really into the field with GPS, collect the information, record it. If you look at many of the Earth observation task or researches, it starts with some idea. Let's monitor wetlands, or let's do the forest monitoring. And you decide, okay, we can do it because there is a Landsat, there is a Sentinel-2, etc. You have lots of images. You have get machine learning models or algorithms, so you can run it. But then when the activity starts, you discover that for such tasks, you would need some training data. And typically, you wouldn't have such. So what do people do? They decide, okay, we don't have training data, so we can develop such using better resolution images, orthophotos, and manual editing and visual interpretation, which is, first of all, subjective because it depends on the interpreter, how decides to collect the points and how decide to label such. And it's time consuming. Imagine how many points can you do per day? 100, 200? And how many points can you do if you go to the fields? I have been working on several such tasks, and we have mapped the whole Czech Republic with such field trips. And if you want to really distribute the points across the country regularly or irregularly, we have discovered that we can do like something like 25, 30 points per day, no more. And if you look what you need for the machine learning, it says it should be something like hundreds, better thousands. If you go to deep learning, it's about 10,000, 100,000, or millions. So every time you run something in machine learning, you are short of training data, or you are not sure about the quality of the training data. This is the weakest point, and most of the people do not care about it, including me. This is the first project I work on, only training data, not only training data, but we dedicated one task to the training data. And if you look at the Lucas, I would segment the European community into three groups. There are people who don't know about Lucas at all. Then there are people who know it exists. They try to go to the web page and try to download some data. Then they got stuck and never use it. And there are few people who passed these barriers and used really Lucas data for the benefit of the mapping. But there are few. If you look at the scientific papers published using Lucas data, I believe there are only two, and the third one is in progress. While if you learn what is the content of the Lucas data, it's really fruitful and probably helpful. Another aspect of Lucas dataset I should mention, if you really start some project and you want to go to the field, you would have the data of the year, but you cannot go to the previous years. And if you are dedicated, if your task is dedicated to change detection, you are completely lost. And since Lucas started 2006 and every year it is repeated, I would say there is a treasure in the data set, which is not yet fully explored and used for the benefit of the project. So this is probably the device to use Lucas dataset, and let me introduce how is it done. So at some point in time, around 2000, Commission decided, let's run operational repeated monitoring of the European landscape. They created over the whole landscape 2-kilometer grid. So every 2 kilometers there is a point which was visited at least once or repeatedly. From these points, they put these points over the orthophotos, which are part of the INSPIRE every 3 years, and started with a simple photo interpretation. So they selected a land cover class to each point, based on which they run stratification. There are 1.3 million of such points over the Europe, and the Commission decided to only visit every 3 years subset of this, which is based on stratification, and stratification is dedicated to monitor the stable land cover and changed. So there are more than 50,000 points that are dedicated only to changes. So after the stratification, the yellow, the white points that you see on the screen, these are those points selected for the field visits. People go to the field. They have got camera, GPS, and instruction what to collect from the field. after they collect it, they put it into database, and some quality assurance steps are performed. So it's a really huge project, and if you look at the whole European landscape, you see that many teams have to work on this project to really collect in 1 year the in situ data. When they enter the field, they first take a photos, 4 photos to this 4 directions. These photos are archived and you can download it, so you can check these photos even from year 2006, 9, 12, 15, 18 now. They first collect the land cover information, then separately land use information, management of the field. Then they collect some structural elements in the landscape, like if you are interested in forestry, you have got the height of the tree and other information about the heterogeneous classes. And 500 grams of topsoil sample is taken out of every 10 points. So there are less, but even for the soil science, there is plenty of information. And they collect photos, as I said. So it's the task is not for 5 minutes. It takes a while. The instructions what to do in the field evolve from about 2 pages form up to really long instructions with diagram what you have to do. It's tough work, but it's still running, and you have got lots of data there. A little bit about the Lucas land cover nomenclature. The land cover nomenclature does not follow the classical European CORINE nomenclature. It does not follow the LCCS. It has its own nomenclature. But if you look at the content, at level 1, it is pretty much covering all the landscape elements, starting from artificial land, describing the urban classes, then cropland, woodland, shrubland, grassland, bare, water, and wetland. So it's everything what you would expect. At the second level, I wanted to point you to the agriculture. Lucas started as agriculture project. So you see at level 2 already greater detail. You have got cereal, root crops, non-permanent crops, and so on. So it is much more detailed than CORINE or LCCS already. And I'm showing here the legend only for the second level. Otherwise, you wouldn't see anything. There are 76 classes. So there's a great detail. And I don't know, it's meant that you would use every class in this detail, but maybe your project would be dedicated to forestry or agriculture, then you can subset these details and keep the other classes at level 1, say. So these are purely land cover classes, but then you have got, what happened? Okay, land use classes. Stopped sharing? Is it back? Okay, we continue. The land use classes are divided in 4 categories. There is a primary sector dedicated to agriculture, forestry, etc. Secondary sector dedicated to energy production and industry. And third one is more about artificial land use. What is interesting, there is the fourth one, which is dedicated to abandoned areas, which is interesting information that is not yet present in any land cover map or land cover monitoring activity across to Europe. If you search into the database, you find that there are more than 50,000 points with this land use specified as abandoned. But there's no product there which would really consistently monitor this topic across to Europe. Sorry. So it is quite a detail. If you combine 76 classes with 41 land use classes, it's a great detail. It gives you more than 1,000 combinations, which is lots of information you can use. Now, if you look at the web pages of the Eurostat, you find lots of information how to download and use the Lucas data. What is the content? You find that the primary data for all the 2006, 9, 12, 15 years are available. You can select country which you are interested in. You can download the PDF files with the instructions, with the field form to see how difficult it is to really fill it and collect the data. You can download the classification PDF, which presents the classification nomenclature, and you can try to work with the data. If you navigate to the database, you find that what you are only allowed is to download the CSV file where the data is prepared, and you can populate it to the database, but the other information is not provided, and there is no running online database that would present such data sets. So let me introduce a little bit of what we have implemented in the GeoHarmonizer project. There is a simplified architecture of the system we have developed. It starts with the persistent layer. We simply downloaded these CSV files, put it in file system, and upload it to PostGIS database. But then we found that there are lots of differences between different files and different years. So we had to perform some of the harmonization process to really make it smooth for over the whole data set as it is developed. We have put on top of this persistence layer, the application layer, where there is the EU data package with a component dedicated to Lucas, and there's the Lucas Python API, which connects to WFS service. You would learn about these services in the next following session. And there is the client layer, which is the interface you would use to get data from this system. First of all, through the Python API, running Jupyter Notebook or a simple Python script, or QGIS plugin. So this is the system which is running online at the moment. Now it's probably time to start the first notebook. So the first notebook is 01 Lucas Access ePy notebook. There's a snapshot from it. If you go to the terminal, and you navigate to ODSE workdir, there is a directory code which has several subdirectories, and you should follow the ODSE workshop 21, which is Git repository, and you should run git pull in this directory, which should download you the rest of the data you will need for this session. Okay. Okay, maybe it was updated for the other sessions as well. I see grass and other. But then you go to Python and 05_ Lucas. And there should be a bunch of files dedicated to Lucas. Okay, let me check the Zoom if there are any questions. Or Valentina, are you? Yes, there's a chat, but I don't see any questions, so it should be fine. Let me go on. So you can start Jupyter Lab. If you start Jupyter Lab and navigate to this Python training 05 Lucas directory, the first notebook is 00 update virtual machine, where you find 2 steps to update the UMap library and update the OWS library. So please run these 2 simple boxes. This is just to make sure that you have the latest version of the software. Okay. Did you succeed to update the UMap library? Okay. Okay, can I proceed? Just waiting for the lady. Are you there? No? Some difficulty?
I'm after the video, so I need to like any changes because of the session yesterday.
Because you have changed some of the training, then probably, maybe Leandro, can you give a hand?
Yes.
Okay, then it's running. Great. So the first notebook is 0.01 Lucas Access notebook. If you open this one, it starts with importing the Lucas classes developed within the UMap library. So if you run this cell, it should import it without any error message. It pass. The first one, just Control Enter. or just run this. Okay.
Can you make your facts larger?
Yes, if I know how.
Yeah, it's with tools. You can try use the tool, but yeah, I think it's working.
Does it work?
Bit more.
Okay, let's go on. So, as I said before, this notebook is dedicated to demonstrate how to use this UMap Lucas package to access the database through the WFS service. So you have imported the important part of this. Then the first part shows how to define a request to be sent to the server. You simply create an instance of the Lucas request class, and you define bounding box with coordinates. You can change the coordinates, but the coordinates would have to be within the EPSG 3035, which is the Lambert equal area, the European definition. And then you can run a method build, which just prints you the request. So if you run it and there's no error message, then you know how to set the bounding box and how to run the request. So the request is defined. The second important task is to download physically data from the server to your computer physically into the file system. You would use the request. You first need to instantiate the Lucas IO class and then run the download method with the predefined request. The third line shows you just to make sure that some points were downloaded, so it counts how many features or how many points in the geo package are presented. So if you run this, it prints you some of the messages from the request. And it says that there are 5,000 something points if you did not change the bounding box for the request. So now you can navigate into your computer and you would see that there is a downloaded file with this. But then if you want to work with this data set, you should set you want to transform it to different formats. You can download it to GeoPackage, but you might want to work with the GeoPandas, directly continue with the machine learning. You can present the GeoPandas datasets to machine learning methods. Here it converts to GML and prints the first 5 lines of the GML. Next one is to store the OGC GeoPackage file. And it prints if the file exists. So let me run this. It says true that the file exists, the GeoPackage file, which is named sample GPKG. If you look to the left, in the directory 05 Lucas, there is the sample GPKG. So it's there physically. Now, a little bit about the request that you can create. First, you can filter by some property in the database. We will use, first of all, the attribute NUTS0, which is the country level for the European Union. So we have selected here CZ, like Czech Republic. So for this, you would need to use the OWS library functionality. So first, the request is created or instantiated. Then you would say operator property is equal to meaning that you are basically creating where clause of the SQL on the database side. But since you are connected to the WFS, you have to compose the request or the filter with the request such a way. So the property name would be NUTS0, which is the attribute in the database, and the parameter is CZ. And you can run build to have some print on the other side. So you see there is the request, the filter is presented. Of course, you want to combine the attributes in some logical way. So let's say you want to download data for Czech Republic and Slovak Republic to have Czechoslovakia back. And so you have to add the logical, which is OR, and you can set the literal, the values of the attributes as a list of the values. So in this way, you can combine any number of attributes and the values of the attributes you want to get from the database. Additionally, you can, of course, filter by years. For that, you should know which years the Lucas data set was collected. So here we go, example 2006 and 2009. If you do not filter the years this way, you would get all the years at once. But you might be interested in changes between 2006 and 2009 only. The bounding box is the same, so you can run it this way. Yeah. Here's the combination of Czech Republic, Slovak Republic for the 2 years. So there is a parameter or attribute in the database survey year. There is a survey date, and we have added extra survey year to simplify the filter. So here you can again build this. And the request is presented here. Then finally, you can define your area of interest. In this case, through the WFS, you would have to present the GML format for the server. And I have to say that for the WFS service, there is a limit of 190 vertices. So your RE should be defined as a bounding box or simple polygon or simplified polygon. So there's example with GML. Next, if you look at the Lucas dataset at the current state, 2018, and if you really upload it from the Eurostat as it is, you would find that there is nearly 100 attributes in the database. And it's because the project evolves and people wanted more and more information. And you find out that you can group these attributes, information collected in the feeds, thematically. It's a land cover, land use. This is the primary information. Then there is one section dedicated thematically to Copernicus, especially for the high resolution layers, some forestry information, there is some inspired information and soil information. And in order to lower the traffic of the data, and you don't need to download all 90 attributes at once, we have created thematic sections. So you can select the groups, Copernicus, forestry, inspired, land cover, land use, and we combine land cover, land use with soil data. So you don't have to download everything at once, or you can, but you can say, I'm interested only in land cover, land use, and you get subset. It doesn't mean that you would get only the information on land cover and land use. There are some compulsory information like the spatial coordinates and other metadata, when the point was visited and stuff like that, that you can divide it. So there's attribute to group it. In this case, it will download only land cover, land use dataset for the selected bounding box. Now, the Lucas datasets are repeatedly collected since 2006, and these are separately in the database. If you want to really aggregate the data so you have got one record for a given point and attributes for repeated visits, you should apply what we call space-time aggregation. So there's a method st-aggregated, which you set it to true and run it. Then it will merge the data set and create one space-time data set. So you can, for instance, use it for the change detection monitoring. Now, there's another example which shows you how to combine different years, bounding box and spatiotemporal aggregation. In this first example, I have aggregated all the collected years. In the second, it's only dedicated to 2015-18. Okay. So this is all from the demonstration of how to use the Python API to access the online Lucas dataset. Of course, you can combine different requests and different filters to get it. Now, let me go back to this presentation. So you know how to access the data. A little bit more of what is the content. I mentioned this already, the thematic grouping. But then if you look at the data set, it covers the whole European Union. It is collected in 2.2 times 2 grid, 1.3 million points. And it evolves from 2006 to 2018. It covers not all countries since the very beginning. At the beginning, there were only 11 countries. I think this covered only the EU 15, or 11 at the moment, and 160,000 points were collected. As it goes in time, you see now we are the last 2 years, 28. And every year, there's more than 300 points collected in field. I should mention that all these 300 something points are in the data set, but not every single point was visited in the field. There are some rules in the definitions. If you arrive to this point and it's not accessible by car and walking distance in half an hour, you skip this point and you do only photo interpretation. If you look at the database attributes, there is an attribute which tells you if it was really visited in the field or if it was only photo interpreted from the orthophoto. Most of the points were visited in the field, but a few of them are only photo interpretation. And as you see, not only the countries were changing, but there were other changes. And the project evolved. So we discovered very early from the beginning that there is a need of harmonization. The harmonization, maybe I should run it. There are a few topics of harmonization. First, if you spot this table, it says that there were only 20 attributes in 2006. Now we have got 97 attributes. So the attributes were evolving. There were some new attributes, some were removed. So you have to decide which you keep. We decided that we take 2018 as a reference. So everything is harmonized to 2018 or 15-18 version. Then attribute names were changing, so there are small changes, but you have to somehow decide which one to use. The most difficult part of this is that not only the names of the attributes change, but the definitions. Typically, At the beginning, there were some continuous variable, like initially there were LC1 PCT, which were the percentage of the land cover in the point, meaning that you step in some point and you see it's not homogeneous one. So you should select to which degree it is this type of land cover. So it can be 90% grassland, but there is a small patch of arable land. So you should fill in the percentage of the main class that you have put. So it expresses to which degree the point is homogeneous or heterogeneous. This used to be continuous variable 0 to 100%, which evolved into LC1 pairs, which is categorical value 1 to 8. And I think number 7 is more than 90%. It is the land cover category you have selected. So given these definitions, we had to somehow harmonize to one version. Data types were evolving. There were some strings and integers differences, and the difficulty in the data set, in the CSV files you download from Eurostat, is that there are many of no data with number 8. There's no definition for the no data. There are many 8s or blanks, and you have to somehow harmonize it and decide what to do with these. So as it evolved, we developed a number of procedures how to harmonize it. This is showing this slide. The graph shows you the pipeline for the harmonization. It's lots of steps. The top is the data set, the CSV files. And we start initially with importing the primary data. Then we found that there are some errors in the coordinates. Some of the coordinates were swapped or some were missing. So we first applied the correction of the coordinates. Then we renamed the attributes with reference to 2018. Then we harmonized the values to the same branch or the same definitions. Then we had to retype some of the values because of the different data types. After this is done, we merge it into one table and we apply the space-time aggregation, which I demonstrated in the previous notebook. So these are the steps you have to take in order to use all the Lucas datasets since 2006 to 18 to have it in one harmonized database usable for your machine learning project. And we think this is a big barrier preventing people using the Lucas data. Now, it is done and you can use it. And yesterday you had a session with land cover model classification model training. Today, for today, we have prepared simple validation with Lucas dataset. We have prepared in the directory sample land cover TIFF file with simple land cover for Czech Republic. We have used the OpenStreetMap as a base for this. And we simply selected the appropriate classes at level 1 for Lucas. So there are 10 classes. So you can find it in this directory. At the same time, I present the Lucas points in a vector file. I think it's not geo package, but the shape file at the moment, but it is the subset of the Lucas points from the database I have shown you. And there is the 0.2 land cover validation notebook, which you can run and see how to run the validation process with the Lucas dataset. So let me change it to Jupyter. So it's 0.2 land cover validation. Now the notebook should open. The first cell just imports what you would need in this process. So starting with OSEs, then GDAL library, GeoPandas, NumPy, Matplotlib to present. Well, I think I've removed this because it takes a while to plot it. one of the most important is to import the validator from validator class, which is the file in the same directory. There is a bunch of methods to run the validation procedure. It's just a wrapper to other functionality based on GDAL and Skylab. And these are convenience functions. So you start it, should import smoothly. If there was some error, then something is wrong, but we double check that it should be running. So before you run the validation, you should configure. In the sample and cover directory, there is a config YAML. YAML is simple text file where you define the key and value. We are using it for many different configurations. I've used it for this type of configuration. Let me show you what is the content is printed here, so we can simply run it. If you run this, it opens the config file. The first section project gives you some names, and important is to fill run ID, which in my case is the date. This is simply added to the directory where the validation log files would be presented for the later use, but you don't need it. The most important is to define the input. You should define the path to the files. In this case, it's sample and cover. You should define the input raster, which is the TIFF file here. You can additionally define the no data value for this land cover product. And the software will simply skip this. Whenever it comes to the point where there is a 0 in the land cover, it will skip it, not count for the validation. Then additionally, you can define legend in YAML file, which is also here. It's very simple legend. You see 10 classes following the level 1 of the Lucas: artificial cropland, perennial forest, shrubland, grassland, barren, wetlands, water, and glaciers, which are not present in this land cover, but it's defined as it is. And then you need to define the vector reference, which is here downloaded the subset of the Lucas point for the Czech Republic 2018 year. And it says L1, so it's level 1, which is consistent with the land product. As the Lucas data, even if you subset the topic land cover land use, then you have to define which attribute contains the information about the land cover. In this case, it's named label _ level 1 or L1 to make sure that you are using for the validation the right attribute. Additionally, there are some validation report settings. You can define in which directory you want to save the report, but you don't have to. And you can select the name of the directory, and it will take this dir name and add the run ID to this, so you can run different exercises with this validator. One extra is setting the validation point for GIS exploration. Whenever you run the overlay of the land cover product and the Lucas points, you compare if it's consistent or not. That you might need it to, if there are disagreements between the two products, you might want to explore in GIS where disagreements happened, and to understand what is wrong in the model or in the data, or to explore really. So you can set the validation point, the file name. It will store in this directory for the report. You can define the data type, OG for the GDAL or OGR format, and you should set the projection. In this case, it's a EPSG code. So this is the settings which you can modify for different projects. You can simply use this config YAML as template and run it with this. So it is prepared. We have done it. Then first of all, you initialize the validator. Validator class takes the config file or JSON with the same content. So you can online edit it in JSON. Later on, we would do it. So if I run it, it initializes the validation. So there is object validation, which has some links and the configuration already. It tells you that there are 2 inputs. You can check that everything is okay. Additionally, there are some convenience functions to check that input data are readable and you can use it. You can open the raster, you can open the vector. This is very simple. Nothing special. Or you can even go deeper and look into the attribute table of the vector. So here I read it as in GeoPandas and I present the part of the data set. So you see that in Lucas data set, there is always point ID, which is unique ID of Lucas data set. You get the survey date, altitude, lat long, knots, observation distance, meaning that it is the distance from the theoretical point created by the commission, which means that the people collecting the data did not reach exactly the theoretical point because it was not accessible, but they move somewhere else. So sometimes it's 0, and sometimes it is, in this case, 22 meters. And you have to be careful with this. If you are using these points for the change detection, you should make sure that the points you use for the change detection should be within some buffer distance. Otherwise, the changes recorded in the Lucas might be changes because of the person of different years collecting from the same data are collecting some other, possibly other land cover classes, because they simply arrive to different point. This is a tricky part. So that's why you have got all these. And then there is an ops type, which is the observation type. If it's 1, it was collected in situ. If it's 0, it's the photo interpretation. Then there is a LC1 pers, which is the percentage. If it's 5, it's more than 50% of the land cover, which you have labeled. Now you see label underscore L1, which is the attribute of our interest. You see here numbers 2, 3. 2 is, I guess, croplands. 3 is permanent crops. But there are some nones. It means that it was not possible to simply translate it because there were some ambiguities. So you have to count on this as well. And the last parameter is the geometry of the points. So you can see it, for the convenience, I printed here the legend. Nothing special, just to know. You can, of course, explore what is the content of the classes. So here's a simple pie chart showing the distribution of the class, the proportion of the classes. You see that most of the classes are number 2, agriculture or cropland in this case. Second, it is number 6, grassland. And then you have got 24%, number 4, it's forest. And there's like nearly 5% dedicated to urban areas. And the rest is small proportion below some percentage, below 5% to say. So you should also check that you are validating, for your validation, you have got enough points. In this case, the number 5, 6, 9, number 5, 7, 9 is not well representative, but it's representative to the distribution of the land cover classes in the landscape where we are running the validation. I commented this part because I was presenting the points in the leaflet, but since there are more than 5,000 points, it takes a while, and in the virtual machine, it's you can see how it is rendering line by line. So you can run it on your notebook, but I skip it here because of the limits. Now, let's assume everything's prepared. You explore your data. You should know what is in the land cover. You should know what is in your Lucas data set, so you understand what is there. And the next step is to run the overlay of the Lucas points over the raster. So there is a function or method overlay. If you run it, it's pretty fast. You find that there are 4,930 reference points. It is processed. At the moment, the object validation keeps the information, and we need to report what is the accuracy. First, there is a simplified short report, which gives you only the overall accuracy information, a number of points which passed, validation failed. This is simplified, but if you run the method report, you would get full information. Still, you see the overall accuracy is about 84%. You could look where the F1 score deviates and what is the support. You would see that the first class has only 58% accuracy, while the cropland and the agriculture, the forest is quite well classified. You can check the producer user accuracy kappa. It's not the biggest accuracy, but to understand really where the confusions happened, you should bring the confusion metric. Before we move on, there is a convenience method save report. So if you run this, you would find that in the directory there is a text file which summarizes what you have done, what is the project, what is the input data, what are the classes, and what are the indicators. So you keep it somewhere saved, not only in the notebook. And you can use it later on. So you save this report and you go to plot confusion metrics. So if you run this, you immediately see that the main confusion is is between class 2 and 6. If you look at the legend, class 2 is cropland, 6 is grassland. As I mentioned before, we use OpenStreetMap for this task. And OpenStreetMap is done by volunteers, and most of the work is done as a photo interpretation with orthophotos. To recognize what is arable land or cropland and grassland from orthophoto is tricky. And there's most of the errors coming from this. So if you see something green on the field, you don't know if it's really grassland or if it's temporary or permanent grassland and if it's cropland. So not surprisingly, there is a biggest error in this. But also there is a confusion between number 1 and the others. Number 1 is the artificial land, but you should learn that in the urban area there are some parks which appears as grassland or forest because there are trees and grasses. So there is also confusion with number 6, number 4. Typical problems of land cover. To get a bit, so this is done. You can, of course, show the normalized one, which normalizes to the number of reference points you have. So this is all done. You can also run the save confusion metrics to have it as a PNG file for some reports and papers. This is all done. Finally, you can run save vec, so it will save the vector with the validation points, and if you open it, what is the time? Yeah, time is running. If you open it, then you discover that what you have done in the validation is saved in the vector. So you've got point ID, you have got the raster value, the vector value, and there's a attribute status which says if if the reference and the land cover has the same value of, or if there is the deviation. So if you select all the zeros where the deviation is, you can navigate to the points where the disagreement between the reference and the land cover is presented, so you can better understand. So this is all saved and you can work with this. Additionally, we can play a little bit with the class aggregation. If you look at this diagram, or the confusion matrix, there is the highest confusion is between 2 and 6. And the true label says it is grassland, but the predicted label or the OSM saying, oh no, this is agriculture cropland. So what you can do to understand is that you merge or aggregate together class number 2 and 6, and you would see what is the value of the other classes. And say, okay, 2 and 6 together is agriculture, and I do not care if it's arable or grassland, it's just agriculture. Okay, let me show you how to do this step. At the beginning, I said that the configuration file can be YAML or JSON or dictionary. So if you copy paste and change a little bit, so the input is the same, you just change the name of the directory where the report would be saved. So I say, I've added underscore aggregation. So it's slightly different test run, let's say. That's it. The other things are all the same. Okay, so if you run this, then you instantiate again the validator, but now a little bit different objects, so you don't mix it. And you present as a parameter the config aggregation, which is the JSON. So the validator now knows where to store the report. That's it. Now we have decided to aggregate number 2 to 2 and 6. So there's a simple JSON. So the class number 2 would be composed 2 and 6. List of the classes. So you create this. And you can, of course, have different, you can continue in this way, but let me simplify it to 2 and 6 to see what is the effect. Okay. Now you run again the overlay. Let's assume everything is all the same. So the inputs are working. And you present this object with the aggregation to this overlay as a parameter. So it runs the overlay with the same number of points. And you can see the report, what is the effect. Now the overall accuracy is 96%, meaning the main problem in the original land cover is in this confusion, and the other classes are quite representative. So with this code, you can a little bit play and explore the content of the land cover, but you also explore a little bit the value of the Lucas points, and really you should do it before you publish something on your research in this way. Yeah, there's the confusion metric that we just confirmed what we know already. Now the next step should be, okay, what is the confusion of numbers 3, 4, 7 with the artificial? But these are most likely the parks or the maybe at the border of the urban area, there are always some small parks which are not used for agriculture, and some products included into urban. But if you go there as a Lucas survivor, you arrive to the grassland, which can be, I don't know, golf course. It is a grass, but then you should really find a Lucas land use that it is used for golf, not for agriculture. So this is the tricky part. Okay. We have got something like 13 minutes. Let me continue. So this was the validation with the Lucas points, but The same way you can use it for model creation, for the calibration, either classification or regression model. Next, what we have prepared a little bit is how to analyze Lucas data. We call it analyze. There are two steps. First, nomenclature translation. As I showed you, there are 76 land cover classes, 40-something land use classes, and then you have got the land cover that has different nomenclature, so you should translate it to this nomenclature. So far, we have prepared the translation table to translate Lucas to Corine, which is not always straightforward. We have taken all 1,400 combinations of Lucas LC1 and land use and find sensible class in a Corine level 3 that would be appropriate for that. Not always the translation is possible, then you would have a none in the translation. So there is one notebook that shows how to use this Lucas class translate, and the second half of this notebook is dedicated to aggregation. I've shown you how to do the aggregation in online validation, but there is another tool, a class, Lucas class Agr, which takes as input the same JSON, but again, you select some code for the label. In this case, it is A00, and you present list of the classes that should be aggregated to this class. So there are two functionalities. Let me show you in the Jupyter. So first you import again from the EU map the respective classes. Then you define the request to OWS library. In this case, Czech Republic, not 2018 year. You download the data. You can show what is the content. There's some warning, but shortly there is some ID, point ID, and you have got LC1 attribute. You can check the statistics of this, but this is pretty much the same as I use in the validation, so the table, the pie chart is the same. You develop your translation table to export the aggregation, and you run apply, which basically takes the geo package and adds another attribute with _A as aggregated, and you can work with it. Here it is, LC1 and LC1_A. Let's show the head of this. So you would see E20 changed to E00. This is the aggregation. C23 is just C00. So the aggregation is performed. It is stored in the file, in the geo package that you can move to your project and run the validation or calibration. Now the nomenclature translation. There's a class, Lucas class translate. You instantiate it with your Lucas data. You set the translation. At the moment, there is one CSV file that translates to Corine land cover, but if you extend this CSV file in the EU map package to other nomenclatures like Urban Atlas, there can be high resolution layers, LCCS, which we plan to do. You could use different translation and use the Lucas data for the validation of the Copernicus products, for instance. So set translation, you say which type of, which version of the land cover nomenclature, and apply, and again, it is stored in this object. You can import it to GeoPandas and present the either of this. And you see here, for instance, the original class is not visible, but E something was translated to 321, which is natural grassland, if I'm not wrong. B something is 211, which is arable land. Okay. Yeah, and you can, of course, download it or save it to different file formats to apply to file to GeoPackage data frame. Okay, this was the translation. Let me finish the presentation. Additionally, there is a graphical user interface. All these functionality to request, filter the data set from the Lucas database, to subset it, aggregate it, and translate it to different nomenclature is available through the QGIS plugin that you find on this repository. Please try to use it and possibly report if you find any issue. We have tested this plugin in the virtual machine. There's some issue with the memory. So you better not using in this with the virtual machine, but in your computer, if you have QGIS installed, you can simply in a QGIS, okay, Czech version, sorry. In a management of the plugins, you say that you want to install it from zip file. You navigate to the zip file where do I put it? Somewhere here. Lucas Download Manager in a zip file. You install it. I didn't try it. This is the first time online I'm trying. And there's a new icon with the plugin picture download Lucas points. And of course, you can select the country you want. Croatia for Tom.
We don't see this
Yes. Yes, I know why, yes. How about now? Yes, okay, thanks for. So what I did is the installation of the plugin from zip file, select, open, install it. Then there is an icon plugin, which I opened. And in the first tab of the download manager, you select the country, for instance, or in a canvas, if you have opened the project and you want just the data for the selected canvas, or you present vector file, here I select the country. I did Croatia. You say you want to detect changes between 2006 and 12, for instance. You are interested in land cover, but maybe other topics, maybe all of them, maybe only land cover. You want to aggregate it because it's change detection, so spatial tape aggregation, and you want to save it to some file, test Lucas GeoPackage, and you run download. And it's downloading from the server, which is at our university. And yeah, interestingly enough, there is no anything. Okay, I've got 3 minutes to go. So it's downloading now. You can also do the class aggregation, which I have shown in the Jupyter notebook. You only have to save the JSON into file, and you open the JSON from the file and you apply the aggregation, which is basically all of the presentation we have prepared so far. So this is it. I just finally mentioned that all the work we have done in this geo-harmonizer project is in a software library, which is at the moment publish as open source the client, but we will also publish the backend as well. So you can run it and you can even change the harmonization process as you need, and you can run it on your own. Okay. Thanks for your attention, and I hope it was useful for you, and you will use the Lucas data, whatever project you would run. Okay, thanks again. If there are questions, we are here till Friday, and we are open to discuss, or at the beginning you see the email or emails to university boxes, so you can post us with emails, or MetaMost is also running. Thank you.
Thank you.
Yes.
I have a question. Thank you for your presentation.
Thanks.
Is there any way to like validate or evaluate the accuracy of the Lucas data? For example, you collect data in the field like what GPS
The GPS accuracy is there in the attribute. It's there. It is attribute of that. You can also measure how far the point is from the theoretical point. That's also there as an attribute.
Yeah, like how far.
Yeah.
There also add like direction. Maybe for example, 10 meters from
the azimuth. You can calculate it as well, because we keep both the theoretical points and the GPS physical points. So this is also there. Additionally, since 2015-18, there are kind of bounding boxes to which extent the point is representative. So there's north, south, east, west. There's a bounding box which says this point is representative for, I don't know, 100 meters to all directions. So it is a plot already. So you can use this. In the methodology, if you go in deeper in the Lucas methodology, you see that some points were collected with a circle of radius 1.5 meter. But if you enter to grassland, shrubland, or these heterogeneous classes, these are defined to bigger area, 22 meters radius. So there are plenty of, I would say, metadata, which gives you together a representativeness of the point, and you can filter based on it. But how to validate Lucas? Well, yeah. Well, if you see the validation process, we store the disagreements, and you can export it with the orthophoto. It can happen that the points where you find a disagreement are located in some heterogeneous landscape. You have got, I don't know, footpaths, then there is a small strip of grassland, and there is a arable land in between. There is a tree, which is typical heterogeneous. And for this, there is the percentage value of the land cover class you have classified. So if you filter out all these, then you have only the points that are well representative. We did not try to validate the other way. Lucas, so you can take the point and go to the field and say where we are, what is it here. We plan to do some ad hoc validation of the Lucas points with the national orthophotos. That's the only way I can think of validation Lucas. But yeah. Just try to think how to collect 300 points across the Europe by photo interpretation and manual work and compare it. And I think the value is clear. Yes, thanks.
There's a question in chat. If you can share the offline version or the visualization version of your slides.
The slides, yes. We will put the slides into the directory.
It's already in the Git repository, so it should be there.
Should be there, yes. Python training, Lucas. The slides are already there twice already. No.
Download it locally.
Yeah, I did, indeed. If you git pull this repository, you should have this presentation in the directory in PDF. Yeah, all the same. Where is the chat? In a Zoom, where is the Zoom? Yeah. Yeah. If it's all, then thanks for your questions and keep watching on the other sessions. Thank you.
Yeah, I go
Can you
to, I
Hello? Perfect. So can we start? So, hello, my name is Martin Landa, and I will be following you now. The workshop is related to using OGC web services in Python language, and after the launch, I will have another 2 workshops related to grass. So let's start. So the first step is the same. You just need to update materials. So because we did some changes just before workshop starts, so please open the folder. You did it many times, so you know. You go to ODSE, work there. You go to code. Here you should have the ODSE workshop, and you just open the terminal here and you run git pull command, which updates your materials. Okay, so let's continue. So we will stay in Python environment. So there are few notebooks, Jupyter notebooks prepared. So you just launch Jupyter Lab environment as you are used to from the previous training session. So there's nothing new for you. So let's open it. So after updating your training materials, which is important, if you go to Python training directory, there is a directory which is called 08 using OGC OWS services in Python. There are basically 3 notebooks, and we will go through. So let's open the first one. First of all, because I'm not sure if you are familiar with web services, or better to say OGC web services, which are which were designed for sharing GIS data or geo data. So all the standards were tailored, or they were designed by GIS professionals. So I'm not sure how much you are familiar with them. So I will just explain very shortly. We have 1 hour and a half, which I mean sounds like a little time, but since you will be not writing, or I will be not writing the commands, it's going to be quick. So we will see how much time we will have, and yeah. So first of all, I will just explain what are OGC web services, or better to say what is OGC. OGC is international standardization, or international organization which is focused on developing standards in GIS field for GIS users, for GIS professionals. They closely collaborate with ISO organization. So many of standards which were developed within OGC organization, they were used or how to say, based on OGC standards, ISO standards have been designed. So there's very close collaboration. OGC is quite big organization. There are hundreds of members. If I remember well, a few years ago it was like 400. There are like big companies like Esri, Google, and others. There are small companies, local or national. There are governmental agencies. There are universities. So the goal is that there will be consensus which will be which will suit for all of us, not only for big corporations, but also something which will be used. So yeah, today we will just focus on few OGC standards. But if you check the website of OGC, there are plenty of standards which are describing like how to work with vector data in digital form. It's called simple features, and many others. Maybe I will just mention two important standards which you already used. It's a GML and GeoPackage. GML was designed and GeoPackage were designed as exchange data formats. GeoPackage should be something which would replace in the ideal world Esri shapefile, but it will take time, and you know how it works in reality. So these data formats you are using, you probably know. So now you can understand better that it's standardized. This is the let's say the most important, that you are using standardized format, which is not vendor lock. So if the case that you are working on in a public institution and you are sharing data with publicly with all users around, you should focus your interest, which format to use, and it should be standardized open format, so that there's no, as I explained, vendor lock. You don't need to use some special software to read it, because the specification of the data format is openly available. So it's okay. I need to take care about the screen lock. Okay, so if you are working in the company, you are implementing the software, you have no obstacles to implement a full support for such formats, because the specification of the format is freely available, and there is a wide consensus how the standard was designed. So big companies agreed, small companies agreed. Most of the members of OGC consortium, they agreed. So this is important, especially when you are sharing. Open data is something now cool, fancy. Everybody want to share the data in a open manner. I remember like five years ago, it was a different situation, especially in Europe, or maybe more years ago. But important is still, to think how to share the open data, and OGC standards is the way, because it's a standardized, it's open. It means that the format is open, not the data itself. You can produce closed data in open format. That's okay. But I mean, for open data, the one requirement or the very important requirement is that you share data in a open data format, which is usually designed by OGC consortium. Well, we will be not speaking today about the data formats. We will focus on web services. We will show how to use WMS service and other services from Python environment. But still, because we have time, I will explain a little bit how the services works. You probably already used some web services, OGC or other. I mean, the word is not only about OGC standards, of course. If you use some proprietary software like Esri, it makes sense to use their own services, because they were designed for the software itself. I mean, if you use Esri web services in Esri environment, it makes sense, because I mean, they designed the services to work quickly, and it's stable and so on. But I mean, if you want to share your data, your data or some processes, tools in an open way, and you you are not sure that all your users can buy specific software, you will use open OGC services, because then you are almost sure that there will be no obstacles, that everybody can access it. We will focus on different web services. I will explain later. What I would like to mention, that besides OGC web services like WMS, you probably know, and maybe you touch WFS. Maybe you were lucky or unlucky, depends on the point of view. You were working with WPS and others. It's good to know that the OGCs, of course, they want to follow trends. There is a new initiative which is called OGC API, which is designed like a response-centric API. So it's not like a replacement for web services, but it's more common, or many people in IT environment are used to use REST API and these kind of technologies or approaches. So OGC API is the answer. So it's not only about, I mean, if you're designing some infrastructure and you want to share data with your clients or with your users, you have different option. Of course, you can publish like data files, which static one, and the users can download it. This is also our case, that we are basically serving in the geo-harmonized project cloud optimized GeoTFs. So this is basically static files. Or you can use web services like WMS, WCS, WFS, or you can use this OGC API to share the data, and not only data, also the processes, the tools that you are able then to perform some tool remotely. You are not running some analysis on your computer. You are just delegating the computation to the remote server. So this is just a short introduction. OGC services or web services in general are designed as the server client infrastructure. There are two sides. There's server side which offers the service to clients. The client can be your desktop computer, your mobile, your tablet, your, I don't know, pocket wallet. I don't know. Now you can pay with everything. So I can imagine that. I mean, in all equipment, I mean, there is no borders. I mean, the client can be any kind of equipment you can imagine, but usually it's computer or better to say application like ArcGIS or QGIS or some, I mean, specific specialized GIS software, because we will be communicating with the web services which were designed for GIS usage. In this training session, I will use another client, which is quite strange, could be quite strange. I will be not using, just to show how the client is communicating with the server, I will not show a specialized, or I will not use this specialized QGIS tool, because they are usually hiding the communication, because the communication is quite scary for the normal user. The client is sending requests usually using the XML file, and the server is answering usually also by sending XML file or data at the data itself. But still communication can be scary. So I mean, if you access, if I will show you here in QGIS something you already know. I guess you were already using some OGC service like WMS. I need to add some new. So let me just copy paste here the map server which we use. So here is the URL. So I go back to QGIS. I will just name it ODSE. I will copy paste the link, and yeah, I need to go back. So I add new connection, and now QGIS is the client. QGIS is communicating with the server. So when I click here and I expanded the tree, somewhere on the ground, QGIS is sending some XML file or something to the server, and the server is explaining, is responding by XML file. QGIS is not showing this file to the user. It would be not good idea. So the server is reading the response and showing to the user in a nice way, not scary one. So you can check, I mean, which layers are here. You can pick up one of the layers. Just take the first, and you can load. So I'm not sure why it's taking so much time, but not a problem. Okay, yeah. So I'm getting the layer. So also in this case, QGIS is asking server requesting for the data. I have problem. Okay, I will put it here because I'm moving too much. No problem. I'm usually used to walk, you know, so that's new thing for me. Okay, so this is the reason why I will be using, just to show you how the communication really looks like. I will show you the communication using web browser, because web browser doesn't know about what it is. It's just showing real content. But of course, I mean, the training session is not dedicated for, I mean, how to use web services in Firefox or Chrome. It's not like that, of course. We will show you how, or I will show you how to use the services using the Python code. But at the beginning, I hope it makes sense to show you how it works. Because I mean, if you don't know how it works, then you don't understand it. You will have a problem and you will not solve it because you don't understand it, what is behind. So I go back to Jupyter Notebook, and there are a few links which helps me. So a few minutes ago, I explained that the client is sending the request to the server. So here is example. Maybe I will try to make it, I mean, the font bigger. So here is basically how the request can look like. I'm not sure why I cannot. Yeah, okay, maybe more. Once more. Okay. We will simplify it in the sense that we will be not sending XML file to the server. We will send requests directly from URL, which is possible, but I mean the software like QGIS and others, they communicate with the server by using XML files. So this is like a simplified version of the communication. So here is the URL. This is the map server, which was set up in the frame of OpenDataScience framework. It has two, as you can see, it has two parts. The first part, or the two parts, are separated by the question mark. The first part is the URL on which the map server is sitting, running, and behind the question mark there are parameters or there's query defined. So by these parameters, you are telling to the server what you want. Yeah, if you want coffee or tea or whatever. In this example, there are two parameters, request and service. By request, this is the most important parameter. By request, you are telling what you want. Get capabilities means that this is like introduction. Client is saying to the server, hello, I would like to know something about you. What is your age? What is your preferences, and so on. So this is like when you meet someone and you want to understand what this person can offer you. And you are telling to the server, I want to communicate with you by WMS service. So this is the same as you start to speak to the person in German, for example. Okay, so you specify the language, the protocol. Okay, so let's try to click, and don't be so scared. You will get the XML file, and in this XML file, I will try to enlarge it. Unfortunately, this server is not well. The metadata should tell you something. Who is running the server? Who is responsible for which purpose? In this case, the map server is performed by GeoServer, and these metadata are default. So this should be changed, of course, because I mean this metadata, or sorry, this map server is not running in Egypt and so on. So it would be nice then, I mean, that metadata say something about the real maintainer. Okay, but if you go down a little bit, you can see, I mean, the list of supported EPSG codes, and you can see also a list of the layers. So there is, for example, layer which is called like this. DTM, hillshade, and something, you can see the bounding box of the layer, and yeah, there could be more information. So you get information which data are provided by the server. So let's go back to the notebook. Yeah. OGC, I mean, till now, it looks like a heaven. You have standards, it's easy, but the reality is something, it's a little bit different. From the heaven, you are in jungle, more or less. Maybe it's too strong word, but anyway, the standards, they are not solid in the time. They are developed, so there are different versions of the standards. And if you compare two versions of WMS, like the first one and the last one, you can see differences. You can, for example, see that some parameters renamed, some parameters were removed, some parameters were added. So it's hard to support all versions of the standard. So this is also the reason why in the request, usually you need to specify which version you will use for communication, because then you are sure that the client will understand the server and the server will understand to the client, let's say, that they will understand each other. To make life easier for Python programmers, the library which is called OWS Lab has been designed. So it really simplifies Python, or the life of Python programmers who are forced to use OGC web services. This is really something which helps a lot. So this is the main message of this training session. I mean, if you want or you need to use OGC services in your code, in your Python code, take a look on OWS library, which do the job for you. Okay. Before we will start web services like WMS and others, we will start with the service which is called CSW, because usually, I mean, when you are searching for data which are available, and I mean you want to collect the list of available data sources for your project, you probably start with a catalog, metadata catalog, to understand, I mean, which data layers or which data sources are available, and so on. Because usually you don't know the URL of the service which is the best for you, so you search. There are plenty of metadata catalogs you can use. I mean, there are different softwares which provide such a service. In the frame of our project, we use Geo Network, which is one of the open source catalog or metadata catalog service-based applications. And by the catalog, or when you want to communicate with metadata catalog, one of the options is that you will communicate in standardized OGC way, let's say. OGC designed for this purpose the standard which is called CSW, catalog service for web. So we will start with this. We will our example is based or we will be communicating with our ODSE metadata catalog, which is basically here available. So we should click. You will get a graphical user interface of GeoNetwork. So you can search by the keyword. I can type land cover. Sometimes the searching works well, sometimes not. It's a GeoNetwork behavior sometimes. So you can search interactively by the keywords or by such some filters you set up. But of course, we will be communicating with a catalog using Python code. So let's go back to the Jupyter notebook. So first of all, if you want to use some Python library, you need to import it. Maybe it makes sense to take a look on first of all on documentation. So here's the OWS library, and you can see that the library is supporting many standards, not only OGC. It's not only about OGC. You can see that there are like US based standards like FGDC, Dublin Core, which is metadata initiative or some kind of standard, let's say. There are things like some Swiss, standards which are strange to me, like a WaterML and others, which I don't know. So and the list of supported standards can grow, of course. So if you want to, I mean, for example, start with a CSW service, you want to communicate with metadata catalog to understand what is available, what you can retrieve, and what you can use. You will go here to the documentation, and you can follow some cookbook. Sometimes, I mean, from my personal experience, sometimes you need to open the source code to understand what is really available. The documentation sometimes hides some issues, and then you need to go to the source code to understand what is really available. And some functionality is quite tricky to explain. I will show you in the first session related to metadata catalog that there are different schemas you can use for communication, and I mean the API differs then. So sometimes it can be quite tricky to find a way. But I mean the most important steps, or the first steps, are explained here, and this cookbook is very useful because here you have here there's explained really the first steps. So the first steps you can do, and if you want something which is a little bit advanced, yeah, sometimes it can be hard to find, but the most important things are explained here, and it's a very useful source. So the standards or supported standards are designed as the Python modules. So here you can see that from the CSW module, I am importing the object which helps me to communicate, or which allows me to communicate with the server using CSW. Later, we will be using other standards. It's the same. I mean, the syntax is the same. You always start. I mean, you type which standard you want to use, and you from the dedicated module you import the class, which is usually the name is the same as the standard. Okay, so you create an instance of the object, or you create a Python object. You define the URL of the catalog service. or catalog, sorry. It's better to yeah. It's not catalog service, it's a metadata catalog itself. So here is the URL. Maybe I will try to this one to no, it's impossible to make it short, smaller, but okay, no problem. So here is the URL, and here by service CSW, you are explaining to the geo network, I want to communicate with you using CSW. Okay, and first we just test, we check if the connection works. So by CSW service, you will get the protocol which is used for communication. If I do typo here, and it will be not working, you will get some scary traceback. As a Python coder, you know that you read these tracebacks from the end. That the most important information is at the end. So you see that it was impossible to connect the catalog server here. So yeah, we know why. So let's fix it. Well, here, no. Here I made typo. So, okay, it works. Now I'm getting CSW as the protocol for communication. And let's check how many, or let's get information how many metadata records are available. I will use a get records to, or the method which is called get records to, which returns records. Just be aware that the library will really get first 10 records. So here you can see that there is 143 records available, and here you have the information that in the memory you have first 10 records. Yeah. So here, if I just print some metadata, I mean, you can print the title. I mean, each metadata record has a title, abstract, who is provider, where you can download the data. So online resources. It can be WMS service. It can be the file, for example, GeoTIFF files or cloud optimized GeoTIFF files. So you can get information. I mean about a specific metadata record. So here I just use for loop. So I loop over the first 10 records which are in the memory, and by the title, by the property title, I'm just printing title. Yeah, so you see that I am getting the first 10 records. You can print what you want. You can print provider. You need to check, of course, the documentation, or you can just try to change title to abstract. If it doesn't work, you check why, and so on. So, yeah. Here, the next example is about how to get all records. So here I just used a simple while statement. Here I'm getting by start position. You can tell, you can define, which is the start position. So on the first run, the start position is 1. The index is starting at 1. So you will get first 10 records. On the second round of the loop, start position will be 11. So you will get next 10 records. So I loop over 10 records, and I'm getting all records. You can loop, the step can be not 10, can be 20, as you want. So it will take some time because you will loop basically more than 10 times. Okay. 14 times. So here I just print, I collected just the titles to the list. And here I am printing the first title and the last title. So nothing, I mean, nothing so useful, but I mean, the important is how to communicate with the server just to show it how it's done. Yeah, this is maybe the most important, that I mean, you are by default, you are not getting all records, you are getting only first 10 records, and then you need to loop over it. Okay, so you can determine, I mean, or by this code you are getting information which metadata records are available. You can get some information about the metadata itself, or metadata records itself. Yeah, but usually you have some goal. I mean, usually you don't want to just see everything what is there. When you use like bigger metadata catalogs, they will have thousands of records. So I mean, it's hard to go through. So usually you want to query. So you have some specific goal. For example, in this case, I wanted from the metadata catalog or my goal is to find the metadata records which could be WMS service. So we specify some query. So here is example how to specify some really simple query. Is here on this line. So you need to specify the operator or the logical operator, not logical one, but I mean here. Okay, I will be speaking about logical operators in the next cell. Here I'm just saying that, I mean, basically I want to search for all metadata records which have everywhere WMS keyword. It can be in the title, it can be in the abstract, it can be in online resources, it can be in provider, it can be everywhere. So it's quite, I mean, it's quite wide filter. You will see that by this filter we will be not so successful, because it will not we will not get layers which have online resource WMS. So this is like example, like the starting point, but usually you need to specify filter which is more specific. For example, if I would just search this keyword just in the title, it would look like that. Instead of any text, I will use the title. But I go back to any text. It should be case insensitive. Yeah. So here I am calling the same method, get records. The first, but with parameters. The first parameter is a list of queries. So it's usually a list. You can combine filters by logical operators, as I will explain later. So in this case, the query is just the first. The query contains just a one filter. Search in anywhere for a WMS keyword. The second parameter is maybe I'm not sure. I think I have old version of the notebook, because here should be something different. So let me check. No, that's fine. Okay, so maybe I just delete it. Okay, the second parameter explains or determines verbosity. So by default, I am trying to get as much as information I can get. So here you see that I'm not getting 143 records. I'm getting slightly smaller number more than 100. And yeah, so you can print the titles, you can print the providers, whatever. Okay, but let's improve our filter. Let's combine two conditions. So the first condition, we are searching for the WMS keyword everywhere it's possible, and the second part of condition will be, okay, I want to limit to the metadata records which have land cover keyword in the title. So basically, I'm searching for land cover layers which I could access by WMS. So here you see that that I'm still using this property equal to. There are objects like property like, which is like operator. If you know SQL a little bit, then you are familiar, maybe more. But anyway, here's important. I am here. The logical operator end is used. So basically, if I would write it in SQL language, it would be like, any text is hard to write, but it's like I will write it like this: condition 1 and condition 2. Okay, so here you combine filter by logical operator, and this combined query you pass as the first parameter, and you get results. Yeah, I need to run this cell. I forgot. And here I run. Okay, I'm getting only three records. So let's print some metadata. I mean, each metadata record has a identifier, UUID, and in this example, I'm printing a title and I'm printing a bounding box of the layer of the metadata record. So here you see that there is land cover, there is Corina land cover, and there is land cover map of Europe. And here are the identifiers. And these identifiers are important because by them you can access the metadata record itself. So if I use the records property, I can also use it as a dictionary. So if I just specify the identifier as the key, then I'm getting specific metadata record. So by this code, I'm getting the first metadata record, which is land cover. Yeah, and I feel that I am really near to get online resource, and it will be for sure the WMS service, and everything will be super cool. Yeah, so I run it, and it's empty. Then I go to Geo Network and I discover there are plenty of online resources, but it's empty. Yes. Then after some time you discover that, I mean, you can specify the schema. So in this way, I'm not sure if it's a behavior. I think it's just Geo Network specific behavior. If there are more resources, if in the case that would be just one, it would be printed, or you will get it. But in the case that there are more online resources, in this basic metadata, it's not provided from some reason. So you can try to be harder, and you can try to communicate with the metadata catalog using ISO standard. You will get really, like, if you would check on the ground now the XML file, which is returned, it's very short. It's like you can read it. It's few lines. It's I mean it's easy to read. It's easy to send such document by the server. It's easy to read it by the client. By this code, by the time names and by the output schema, I'm using ISO metadata standard, which is 19 something. I don't remember the number now. I put it to the notebook, but probably I haven't uploaded, or I haven't pushed it to Git repo. So after this this training session, I will do it. And if you check what is the file, the XML file which is sent, it's like 10 times longer, and it's super hard to read. So this is the reason why it's not by default, because the metadata catalog need to create such file, which is very complicated and very long, and the client need to read it. But this is the way how you can get these online resources in the case that there are more. So let's try it. And this is even what is worse than if I change the output schema which is used, then the API is changed also. So here in this default output schema, I was using references to get online references. When I switch to output schema or ISO output schema, I need to use another API to access the same information, which is not, how to say, I was not satisfied by that. Okay, so I'm getting the links, and this is bad news for me because I see that I can easily see that the WMS filter on any text was too generic, because then when I check the data, there is WMS keyword, but it's mentioned as the URL for the legend. So I'm getting online resources, which is fine, but there are TIFF files. So this is not a WMS service which I would like to use. But I mean, to show something, of course, here is the link we can use. So, but I mean, in the best case, we should get this information from metadata catalog. So it will be probably improved in the future. But I mean, this is just a showcase how it could work. And to emphasize that, I mean, it's important to specify filter which is not so wide. I mean, which is more strict, and then you will get metadata records which really fits your requirements. Okay, so this is usually the first step. You connect to the metadata catalog, you search for data sources you can use, and you collect suitable data sources for your purpose, and you use them. Okay, so we found a map server which is providing the data we want. It's ODSE map server, which is available here. It's performed by GeoServer, but I mean, we will be not using, of course, the web interface. We will communicate with the server using Python. Okay, so here is example. I mean, if in the case that you would communicate just really in a hard way using web browser, you will get the XML file, get capabilities. This is the introduction. But again, it was explained and the time is running. I thought that I will be quick, but I am slower and slower. So let's speed up. So I will be communicating with the server using WMS. So it's the same approach. You just from a WMS module, you import object web map service, and you just set up by the URL. And then you can get immediately metadata. Yeah, and as we could see at the beginning, the metadata are not filled properly. So, but yeah, but you can get them. Yeah. So here is the title, here is the abstract, here is the name, and here is the contact. So you can contact none if the server is not working, which is fine. Yeah. So let's continue. So you basically get metadata information from the server, and you can, by the content, by the property content, you can get information which layers are available, and this is important. Yeah, you want to know which data are provided by the server. So you get the list. Maybe I can, yeah, there's plenty of layers you can access. So you choose one. I choose land cover product. So here is the name of the layer, and by the contents can be accessed like the dictionary, and the key which is used is the name of the layer. So here you can get like a bounding box of the layer. You are getting bounding box in European terrestrial reference system, and you are getting bounding box in WGS 84. Yeah. Okay, so you can determine which layers are available. You can check out. You can check metadata, which I mean the relevant metadata for each layer, and then by get map request, you can request for the data. So this is basically what QGIS was doing when I was showing at the beginning. So when you expanded the tree, QGIS sent get capabilities request, and if you just add the layer to the map display, QGIS sent the software sends the request get map on the ground. If you zoom, if you pan, it's always get map on the ground. Yeah, so here's basically how this request would look like from if you would run it in crazy time in web browser. So you will get basically image. Yeah, the WMS service is returning not like a data itself or the data you could use for computation. You are getting like a preview, like map composition of selected layers. So it's usually, as you know, it's usually a service you will use to get some base maps and just to show them on background. So here's how you can get data using OWSLib library. So here is the get map. You are specifying which layer you want to display, or which layers. It can be like a list of the layers, and you will get a one image with a layers composition. So here you specify the size of the image, in which coordinate system the image will be rendered. And here you are specifying the bounding box of your area of interest. And here you are telling to the server in which format you would like to get the data. So basically, if you compare this URL with this Python code, it's doing the same. So here I'm just showing the image interactively. Wow, okay. Yeah, I forgot again to run this cell. Well, the mouse is not working well here, but okay, it works. And here is the similar example. I just changed my bounding box, which points to the former Czechoslovakia, more or less. Okay, so this is example how to access WMS service, and let's continue with others. So the second notebook is focused on WFS service, which is a similar service as WMS. It's providing data, but it's not the service which provides some preview or map composition. It's the service which is providing real data you can use for your computation in GIS. It's vector data, better to say. Usually, WFS service returns GML, which is, I mean, quite. It's not surprising because, I mean, if you are using open service, you should get open data format, right? But it can be everything you can imagine. But usually, it's GML. So. As a demonstration, we will basically use the WFS service, which is providing harmonized Lucas data. So, I mean, if you follow the previous training session, we will be accessing the same data. We will just not use the EUMAP API, which simplifies access. But we will be using really the OWSLib API. So you will see how it works really behind. So the same thing. What is I mean, which is nice, that I mean the OGC services like WMS, WFS, WCS, WPS, which I will present as the last part. They have many things common. They were designed by the goal to behave in the similar way. So all these services, they have get capabilities request, which is like, as I explained, some introduction that, hello, I'm here, the client, I would like to know what the server offers to me, or what you can offer to me. So this is basically the same style of URL address which we used when we were accessing WMS. So there is the URL of the server. And here are the two parameters. The first parameter is request. You are telling to the server what you want. And by the service parameter, you are telling to the server which protocol, which language you want to use for communication. So the same, nothing new. We just use WFS module. From the WFS module, we import web feature service. And yeah, we create the object. We need to know the address of the service, of course, so we will find it in our metadata catalog, and we can access it. So here I just print some metadata. So who is providing, which is the title keyword, and you can see again there are some basic metadata which need to be improved. So this is the second map server without metadata setup. So this is the reason for me to fix it, at least here. So yeah, so here you can get, I forgot again to print cell. So here you can get the URL address. Yeah, okay. And by the content, so the same approach as we use in WMS, there is a contents property, and by this property you can by this property, you can get information which layers are available. So here are some default one, which are not clean up. But what is important here are the lookups. And you see, if you remember, you access in a lookups training session different like classes, groups. Sorry, you are working with a space-time aggregated data, so you can see here how it really how it's implemented. That I mean, each group has this view, or this is the separated layer for each group. Here are the space-time aggregated data, and so on. So here are the layers. Yeah. So now you know which layers can be accessed by you and consumed. And now the last request. Just remember, in when we were speaking about WMS service, we used get map request to get the data. So here we are not getting map. It's not web map service, it's web feature service. So there's like consistency. The request is called get feature. So I want to get vector feature or features. So if I click here, I'm getting features. There is some limit. I think I will not get all lookup points. It's like 1.7 million of points. I think GeoServer will return just the first part, but yeah. But you should you see that you are getting some coordinates here. It's not yet highlighted by Chromium or Chrome, but you see that it's GML file somehow, but it's not rendered well. But this is not important. Let's go back. Yeah, and let's do something more relevant. We don't want to get all points or lookup points. We want to use some filter as you did in the last in the previous training session. So we basically use the same filter which we used like 1 hour ago. So here I am identifying which layer I want to access. So I want to access the layer which is called lookup points. And you see that the API is the same. Yeah, you know, if you remember when we built the query for the metadata catalog, we use the property. I made them. Yeah, we use the property equal to. Here I am using property is like, but I could use property equal to. It would have the same result. So basically, it's like a var statement, or if you, I mean, in QGIS or ArcGIS, if you just load the vector features, you go to attribute table and you just specify a filter based on attributes. In ArcGIS, it's called, I think, selected by attributes or something like that. So this is the same. So here I'm just telling to the server, okay, I want features from you, but I would like only those who have in the attribute nuts 0 the value CZ. Yeah, this is quite okay. It's not tricky. It's explained in the documentation. You need to decode. This filter to XML to the XML schema or form, and then by the get feature you basically run get feature. Yeah. So here you are specifying the filter. So you should get only points, lookup points which have CZ in a nuts zero attribute. And yeah, I'm not showing this data in the Jupyter notebook interactively. I will just download it or store it to the on disk, and we can display it in QGIS. Okay. So if you run this, you should get the data GML here. And if I just open QGIS, and yeah, if you don't see browser here, you go to view, I think, panels, and here you can enable browser, which is quite useful. And yeah, I go to home, I go to ODSE work there, code, workshop, Python training, 08 something, and here I should get the GML file, so I can just load it. It's in this virtual machine, it's a little bit slower, everything. Even my laptop is quite good. Yeah, so here I am getting the points of Lucas points, which are located in Czech Republic. And yeah, I can go to the attribute table, and you can see that all records have in nuts zero attribute to CZ value. So it works. Yeah. So let's go back. Okay, I have 15 minutes. That's fine. Okay, I'm surprised that it works. The timing. Okay, WPS. WPS is a service which is a little bit different from the point of view. I mean, what is server providing and what you could get. Yeah. WMS, the WFS, which we just demonstrated few minutes, dozen minutes ago, the services are providing data. So we are getting data. You are getting image preview, map composition. You can, or you are getting vector data. If you would use web coverage service, you could get raster data with real values inside, not only preview. WPS is different in the sense that it's not providing, okay, you can get data, or you are getting usually data, but the data are created dynamically, not statically. I mean, the WMS, WFS, WCS are based on static, usually static data. There is some database behind, and I mean, the service is reading data from the database and sending data to the client. But usually the service is not computing anything. It's just accessing data which are available, which are prepared. WPS is providing tools, so you can launch specialized tool remotely, which is very useful. I mean, if you are in the field and you are collecting data in the field, usually you are not taking with you the powerful server on your back. You have a smartphone, you have a tablet for collecting the data, and you want to compute directly something based on your measurements. So this is the way that, I mean, you send collected data to the dedicated server, and the dedicated server will perform the computation, and you will get result. Result can be one number. Result can be the vector features, vector data. A result can be whatever. It can be image, it can be video, I don't know, whatever. So it depends, I mean, what the tool is doing and what is the result. So we will use again the demo service, which is provided by geo-harmonizer project on dedicated server. It's running here. Basically, there is also You can in this Git repository, you can see how it's implemented. Basically, there is only one tool now, just for demonstration. There are not more tools. There is only one tool. Tomorrow, my colleague Salim will have presentation about air quality data products which we are providing. So basically, this tool is computing space-time or it's performing space-time aggregation, and you are getting like this air quality product in a given time range. So you specify the start date, end date, and it computes the aggregated product for your usage. So this is really demonstration how it can work, and you can see how it's also implemented. It's running in the server in isolated Docker environment. Yeah. Okay. So let's go back again. Nothing new. There is a request get capabilities, which you can use. I mean, in the same way as we used. It's just a introduction. Hello, I'm here. I would like to know what you can do for me as a server. What you are offering. So if you click just for fun on this link, you get some metadata information. This is the first case the metadata are real. So here you can call me to my office. You can send me the mail, and so on. If it's not working, please. Yeah. But still be aware, it's demo. It's just a demo service. It's not designed to be in production. Okay, so how to access? Nothing new. You use WPS module. You create a web processing service object. You define the URL where the service is available. And you get capabilities, and you can print some information. I mean, I'm printing a type, title, and abstract. So it's printing these three information. Yeah. So it's WPS service. Here's the title, and here's the abstract. So abstract doesn't differ from the title so much. Yeah. If you remember WMS and WFS services, we were using contents property to get a list of available layers. Here, it's not contents, it's processes. Because I mean, the service or the server is not providing some content data, it's providing processes or tools. Yeah, so here you can see this server is really minimalistic. I mean, if you like music of Philip Glass, for example, you enjoy. It's really minimalistic. There is only one tool available. But of course, normally you have plenty of tools available. So let's try to get some detailed information about the process itself. So for this, we will use a request which is called describe process, which describes process. So you will get information. What are the input parameters? What are the output parameters, and so on. So again, if you are not still scared and you click here on this link, you are getting this XML file, and you can read it from that. But this is not our goal. Of course, we want to get these information using Python code, Python API. So from the WPS module, we will import a helper function which is called print input output. It should be here. Yeah, it should be. Okay, never mind. Okay, here. So I will use print input output, which is like a helper function which nicely prints information. But of course, you can access input parameters as the objects. Each parameter has the title, abstract, default value, and yeah, other informations. But I mean, in this case, I use this helper function to print it only. So here you see that there are two parameters. First one is the start date. The last one, the second one, is the end date. Yeah, it's just a string, so there is no validation performed, or the validation is performed in the tool, but basically it's string. Yeah, and in the same way, you can get information about the output parameters. This tool is really simple. You have only one output, which is a diff file. So this tool will return to the client a diff file, raster file, with aggregated PM 2.5 values. Yeah. So now we know about the tool itself, what it is, how to use it, what are input parameters, what are output parameters, and we can execute the process. So here in this example, again, I put the corresponding URL address, which would do the same. So request is execute. Identifier, you need to tell to the server which tool to execute, and by the data inputs, you are defining input parameters. So here is the start date and end date. Just be aware that this tool currently is providing the data only for the year 2018. So if you choose another date, you should get the error. So how to do it for using Python API? So basically here you define the list of the input parameters. The list contains tuples. There are two items. The first item is the input parameter, the name of the input parameter, and the second value is the value. Yeah, is the value. Value related to the specified input parameter. So here I am calling execute. Yeah, you can see that the methods are usually called by or the name is inspired by request itself. So here you specify which the process ID I define here. So I will use the tool, which is the tool which is provided by the service, and yeah, and here I am sending inputs, and here, yeah, it's a little bit maybe confusing. The output must be specified here. It means that you are interested to get output afterwards, which is quite normal. Here by monitor process, I'm telling to the library, wait, I want to wait for result. Okay, this is important. So it will take some time. Yeah, I forgot again to launch this cell. And now I can go here, and and this is the first time I'm really executing tool on. And now, yeah, I'm now afraid a little bit. I forgot about one thing. In the configuration, there is a maximum processes running in parallel, and I'm afraid that we can exceed it. But okay, let's hope that I will be one of the first who will launch it. So yeah. Okay, so now I have data, or no, okay. Now I have, or the library has in the memory the XML file which is returned, not the data. because I mean the output, there can be more output parameters. So now the library has the information where to download data. So by retrieve data, and there is only one output parameter. So this is the reason why I use 0 here, because it's a list of output parameters. I know that there's only one. So by the retrieve data method, I'm really downloading data or output data from the server. And this file I will store in the current directory. And yeah, using raster.io, I also display, but I mean, it doesn't look nice. It's better to display it in QGIS. So now I'm getting data. It can take a time because the data can be, they are not so big, but it's like a few megabytes, I guess. So QGIS. So here is the output, and yeah. Yeah, I will switch to 3035 to avoid the reprojection. And yeah, and I zoom to the layer, and I should get the data. No, I don't see. I see strange drops. Wait, no, that's strange. I choose strange. I choose. Yeah, the legend issue. Thanks. Yeah, there's some issues. Legend, probably. This is strange because I tested and it worked.
You just go to put it to single band pseudo-color.
Okay. Okay. Thanks. Thanks. I need to take a look and fix it. So I go to symbology, right? And I go to single band pseudo color, classify. No. Okay. Strange. It should work. Yes. Yeah. Okay. Now in grayscale, I'm getting the data. So something changed in the server. Okay, but you see that in gray color, I'm getting the data. Yeah. Okay. The last point I want just to mention that usually as a client, you want to execute the process not okay, I will not say this word because I will make a mistake, so please read it. It means that that you, as the client, you will not wait for result, because it can take few seconds, but it can take few minutes. And I mean, the tool can do some super magic, and it can take time. So the tool can compute few minutes. And I mean, it's hard to keep connection between the client and the server for a longer time. And if the client will lose connection with the server, there is no way to, I mean, the server will not understand who sent the request. And when the client connects again, there is no possible to pair it or to continue in the communication which was established few minutes ago. Yeah. So in this type of communication, client sent the request to the server. Server immediately responds by the XML file. I know about you, that you requested. Here is job ID. So the client will get job ID, some unique identifier, and client can send like every 5 seconds request to the server, and the server explains, yeah, I didn't start it because there are other people, other clients in the queue. You need to wait. Or I started and it's like a 5 seconds, a 5% computed. You need to wait. So then the client can have a nice progress bar and can show what the server is doing. So this is example how it can be done in WPS. So I basically designed my own monitor execution function, which have the file while statement, and it's just every 3 seconds it asks the server what you are doing, and I'm just printing some message and so on. Yeah, so let's try to call it. I hope I will be lucky again that the server is not full. Yeah, so you see, okay, it's not so informative because you will see that this person more times, but I mean, it depends how designed the tool is. So here you see some progress of the computation. Yeah, but usually, I mean, most of the users will use some graphical client, like in QGIS. There is a link to the one. There are 2 plugins in QGIS for WPS. I'm here demonstrating the tool where I'm involved. So here you can see the progress bar, and it can show nicely, I mean, the progress of the computation. Yeah. So that's all. I am really, yeah, it's surprising for me that I manage on time. So it's 12:30. I should finish, right? Okay. Yeah, sure. And I should check afterwards the Zoom, right? That in the case that there are questions. So please, if you have question.
Yeah, it looks very nice to put this in the use it with Python. I was wondering, so could a use case be to use it in machine learning, like to use these services to gather variables for making predictions, or would you recommend this to use it this way?
Well, it depends. I mean, if you want, for example, training data, and I mean, you can retrieve training points by WFS service. You can directly transfer it to GeoPandas, for example, structure. This is basically what we did for Lucas API. That I mean, OWSLib is behind. I mean, it's the engine which is performing the communication. But okay, we retrieve, or you will get from the server basically GML. So you need to somehow read it by GeoPandas to get the data frame or some desired data structure. I mean, I can imagine processing services which could enable users to run machine learning on, I mean, some good machine, good hardware. But of course, it's there are security issues, you know. So it's, I mean, this is the reason why usually you are used to use WMS service, because it doesn't provide real data, but still there are security. I mean, if you provide such service to the public, the important is, I mean, how to build a technical infrastructure, because I mean, if you are providing data which are accessed by many users, it can you can have easily problem with technical infrastructure if you are getting like thousands queries in parallel. And I mean, these processing services, it's highly insecure, because I mean, the client is sending data to the server, and in the data package, it can be everything you can imagine, something which is dangerous for the server. So I mean, to provide these services, like just that you play this, it's quite easy, but I mean to run it, or to have or to to have production environment, it's it's challenging because you need to solve how to build a technical infrastructure. If you have more queries, there must be some horizontal scaling. That I mean, you have some Kubernetes, for example, behind, and there are security issues which can be very dangerous for the servers.
As a server.
Yeah. Yeah. I mean the client is on the safe side.
Yeah. Okay. Can you give us some examples of like big organizations that you use?
Well, WMS service or WFS services are quite common, right?
I mean,
Yeah. It's usually such geoprocessing services are not provided publicly. Usually, that the companies are providing such services just to the clients who pay and who have limited access, of course, or internally in few governmental agencies or some institutes. I mean, which are providing such services, but only to the clients they know, or the limit is, or the access is usually limited because it can burn out the server very easily. Yeah. I mean the server application, for of course it need to be prepared. That I mean, if you get too many requests in the same time, there's a queue. So I mean, yeah, there are possibilities how to solve it, but still, if you want to produce, if you want to run such services in production, it's very challenging. Yeah. Okay. Thanks for question. So thanks for attending a lot. It was nice to have some people here in the room. Thanks a lot. Where I have the Zoom? Here. Okay, yeah.
You can share.
Okay. Good afternoon. So we will start the second block of the day 2 in this training session and in the context of the OpenDataScience Europe Workshop. And in this session, we will explain about the cloud optimized geotiff. So the title of the session is really working with the cloud optimized geotiff in Python. And we will use the notebooks that we provided. And we already used it in the past sessions a bit of the cloud optimized geotiff files. And it's important to emphasize that all the outputs, the raster outputs that we are producing in the context of the OpenDataScience Europe are cloud optimized geotiff. So what we will present here, actually, you can use for all the data that we are generating. And so my presentation, in my presentation, I will provide a short introduction to this format. So we call it, the acronym it's COG. And we will use it, we will access it in QGIS and show how to do it in the GDAL. And so actually GDAL, it's the base library that implements this, the access to this file format. And now it's a more like a combination of file format and access protocol. But if QGIS, raster.io in Python, all these softwares and frameworks, actually they use GDAL on the end. So, and to the Jupyter notebook, we will do an exercise to clipping region of interest and to calculate a time series access, so how to access data. And later, the end of the presentation, we will discuss about the stack, and we plan to implement it in the project. And we believe that it's a nice protocol, a nice solution to put all these cloud optimized geotiffs available. So what is cloud optimized geotiff? So it's a regular geotiff. So, and if you think about the geotiff, TIFF actually it's an old format to save like raster data, images. So I think it was created in the context of like image processing and photography. So, and we call it like a less format. So you can compress the data and you can save it. And later you need to decompress. So you have the original data after the compression. So you don't lose any type of data information related with the file format. And on top of it, if you work with geospatial data, for sure you already saw some geotiff images. So on top of this format TIFF, it was developed the geospatial extension, so to embed the informations about the projection system and the size of the pixel and spatial resolution. And so cloud optimized geotiff, it's a kind of advance and evolution of the geotiff. And if you think, here are the three aspects that make this format really like special and really useful for the most part of the applications today. So it is a less compression. It implements it. It provides tiling and overviews, and you can access it through HTTP range. So, but what it means? So, this format was specifically developed to work in a cloud environment. So, when you are in a cloud, you need to minimize the access to the data, because if you move your data around, you will lose some performance, and you if you minimize it, you can really optimize your workflow and access and invest time in the computation time. So this format, the first part of it, you have the different possibilities of compression and what this compression means. So in the last session, when we loaded that tile that I presented just for our pilot tile, you have more data in memory than in disk. So it means that when you save the data, like that matrix, if you think in a raster data, it's a matrix, could have multiple bands or not, but you save this matrix in a compression format and you compress it and you save in the disk. So it will occupy less space than in memory, but you have a cost to do it. You need to run some type of compression algorithm and you encode the data and you save it. But when you need to load it again, you need to decompress. So it's like a zip file. So, and to decompress, we also need to run some decompressor, and it will take some time. So a good format, a good compression format, it's actually, it provides a good balance between of it. Because if you compress too much, probably it will take more time to decompress, and sometimes it's not good for your application. But the most common compression formats that we have available in the GDAL implementation, it is deflate and the LZW. So and you can just select this format when you save your GeoTIFF as using GDAL, and you can see that the file is maybe 5 times less. The files you save the file with occupying 5 times less space. And so this is really important because, of course, it will minimize the data transfer between the cloud in a cloud environment. And the second part, it's the tiling and the overview. So when you have like a big GeoTIFF, so imagine our GeoTIFFs for Europe, we have more than millions of pixels, but maybe you are just interested in a part of that pixel, so that image, so just part of the chunk of pixels. So if you have just one big chunk of data saved in the disk, you need to load everything, decompress everything, and sometimes it doesn't fit in the memory, for example. So the tiling, it's actually a nice way to split the data in regular grids, as we are doing in our processing workflow. So you can define a tile size, so it could be 1000 by 1024 by 1024, but it's just a regular grid that you will split the data, and you can access parts of this data just recovering from the disk, just these parts. So, but on top of it, specifically like from the cloud optimized GeoTIFF, you have the overviews. So considering this tiling system, you can provide like a downsampled representation of this image. What it means, if you think in the whole image that we have now for Europe, maybe you just want to visualize it, but just to visualize, you need to load everything in memory. So it's possible actually do a type of pre-processing to load it and generate like a short version of that image with less spatial resolution. So instead to use all the pixels, you need to use all the pixels to generate it, to have like a reliable representation, but you just have like now a shorter image. with less pixels. So it's a kind of, I don't know, instead to have a 30-meter image with 30-meter of spatial resolution, now you have 1 kilometer of resolution. So it loads way fast, but all these concepts that I'm explaining to you, it's already inside of the format. So GDAL manage everything for you. And using these concepts, if you put this file compressed with the tiling system and with the overviews calculated, you can put in a web service or a kind of HTTP file service, and you can access it through the network. So, and with the network, you can access using this range request. So instead to access the file locally in your disk, you are just accessing like a URL as we did in the last training session, but now we will do it more and you will see how it works in a practical way. So basically the cloud optimized geotips, it's a combination of all these concepts. So, and more recently, you can use it and host like in service like S3 from Amazon or hosting in Google Cloud Storage. So instead to have it in like a web service or put your own server, you can use like services that are specifically designed to provide like data through the cloud object format. And mainly, the difference between the file storage and cloud storage. So file storage, it's the file system that you have in your computer. Each folder that you enter, you will like enter in new folders and you can see the folders, the data. So actually the data is the files, your files are in the last part of this tree structure. But here in the cloud storage, it's a total different concept. You just have a chunk of data and you put it on the type of service and you can access it through some URL, but mainly you have a unique identifier. So you avoid all this navigation across the file storage. So the best way to use the cloud optimized geotiff today, it's really hosting a cloud object service like S3 or Google Storage. But of course you can host it, you can have in your own machine and see it, but if you are managing like and dealing with big files, it's better provided in a cloud environment. So and today we are seeing like we are seeing a lot of like the big players are really using this format. So USGIS, for example, they provide all the this book explaining how to access the Landsat data through cloud optimized geotiff. And you have this system in the Google Cloud. Now you have available also Landsat data and Sentinel data. So, and all these files are available through cloud optimized geotiff and in cloud object storage. So there are multiple possibilities to access, for example, the Landsat data. And you have also in the AWS, so it's the same archive. And of course, these cloud providers are really interested in put this data available to allow and other applications to be developed inside of their infrastructure. So for example, if you have one processing workflow that use, for example, the original Landsat 8 or the Sentinel, and if you put all your code inside of a server in the AWS, you will minimize all the traffic and you can do a lot of processing and just downloading the output, for example, like a land cover classification or a pre-processing for the Sentinel and the Landsat data. So, and in the context of the open data science, we also are using like these cloud optimized geotiffs, and mainly we are processing all this data in different servers, like local servers, cloud servers, but the production of the cloud optimized geotiff, it's mainly with GDAL. So we all the files that we are providing here in the Open Data Science, they were generated with GDAL, and it's important to emphasize that the GDAL used was the version. Actually, here it's equal or bigger or equal 3.1. So it's when the cloud optimized GeoTIFF driver was really implemented and released in the stable GDAL version. And so we generate these files locally using our servers or other servers, but locally in the server. And later we send it to, there is a self-hosted cloud object service. So it's compatible with S3. And it's a kind of S3 that you can self-host in your own infrastructure. And we have the Wasabi. So it's a cloud-based object storage server. It's really similar to the Amazon, but it's way cheaper, and it's compatible with S3. So right now, our data is in this Wasabi, and in our local infrastructure hosted in MinIO. So, and what we will do during this training session, it's mainly access the data that it's available in the Wasabi. So I will provide some URLs and some instructions of how retrieve this data and how work with that and what are the advantages, and all these concepts that I'm explaining, you will see working in a practical way. So to start, first I will, so this is a screenshot from our web viewer. So the first thing that I would show is if you click in this link, it's the same link that I presented yesterday. So mainly this this image here is the Landsat RGB mosaic generated for 2019 for the summer season. So summer, it's the best mosaic that we produce it because it has less cloud interference. And if you play with the opacity, you can just see the other layers here. And it's available here. So this is the RGB Landsat. So it's a file with 3 bands, red, green, and blue. And you can back in the time and see different years. So each year here, it's actually one different file. So we generated this cloud optimized GeoTIFF for all the years. And actually it's a 3-band, and specifically this file, after all the compression that we generated, it's about 10 gigabytes. So it's a big file, and to work with that, you don't need to download everything in the old-fashioned way. So what I will show now is we have this URL here, and you can copy this URL. So the first exercise here will be open it in the, I'm outside of the VirtualBox. I'm just, yeah, here. Okay, it's here, right? This is the QGIS. So what we will do now, it's mainly get this URL and open in a QGIS as a service. So, because for example, in the QGIS, you have that plugin to see, for example, Google Maps, to see Bing Maps, but it's also possible access. Okay, good, thank you. It's also possible access cloud optimized GeoTIFFs. And one thing that it's important, to generate cloud optimized GeoTIFFs, you need to have a new version of GDAL, but it's fully compatible with like old versions. So actually to access it, you don't need like a really new version, because GeoTIFF, it's a pretty standard format, and it's fully compatible. So what I will do now, so let's get this URL here. and we can copy it. So it's a land cover, RGB, Landsat GLAD, percentile 50, and we just put the summer images, but this is an image from 2011. So, and now here, add layer, raster layer, and in QGIS you can open like a raster layer locally here, but you have this protocol HTTPS cloud, so mainly we will use it. And again, this will be executed actually by GDAL that will access this file and bring the result for us. And don't be confused, this is not a download. So it's actually like accessing part of the data. You need to remember that this data has 10 gigabytes. If we download it, maybe it will take the whole session. So actually what we did several of pre-processing and using this cloud optimized GeoTIFF, preparing the data to allow to the people access just part of it. Just an overview, just, I don't know, some pixels located in Wageningen, and these libraries and this software in some libraries can manage it and access just parts of the data like in a really seamless way. So if you add it here, it will can take not too much time, but it's not as the same faster as same in your machine. And yes, the first thing here, I will disable this functionality. The first thing is you can see that it's just a more like a black image, but I really don't know about it, and I don't understand, but when you load a cloud optimized GeoTIFF, for some reason, QGIS doesn't enable this contrast enhancement. So you need to enable it, and you need to select this because it's a nice way to apply like a enhancement. And if you, and to enhance the data, if you need to click apply. So now you, actually it's basically a histogram stretch to these values here, and it will provide a better contrast to see the image. And if you click here, you have the same image. So the first time that you load, it's not enabled by default in QGIS. Maybe in other version it is, but the versions that I'm using, it's not enabled by default. But you can see, you just change here, properties, enable this stretch to min-max, cumulative count, and now you have a nice image. So, and okay, and with these images, so this is not a WMS service. It's not like any of these web GIS servers. It's actually real data. And you can see that because if you enable this plugin here it's you can use this plugin that we set up. So here, you can actually access the pixel value. So, and we are talking about 3 bands here, red, green, and blue. And those are the pixel values of these bands. So the spectral values rescaled to a byte format. So it will, the range will be between 0 and 255. So this is actually real data, and you can zoom in. And if you zoom in some place, so you can see it will load. So it's almost the same speed of a local image if you have it. So sometimes it's almost, it's the same speed basically. And so, and you, again, you can check its full resolution. So this is not like something as Google Maps service or something like that. It's you are accessing the data. But what it's happening here, like behind of this type of magic, each time that you zoom in, you are seeing like a part of that layer pre-computed, like that pyramid layer. So this image here that we are seeing, that it's not the full resolution image, because it's not necessary bring all the pixels. I don't need to have the full resolution of this image to provide an overview in this scale and in this level of zoom. So what is happening here, all these pre-visualizations and these overviews, that pyramid layer that I show in the slides, it was pre-computed, and now QuantGIS, it's just accessing the different levels of these overviews. And we will access it in Python. So you can see the same thing in the code, but here it's happening like by the library, like inside of the software. And it's why it's fast. And mainly this concept actually, by the way, it's the same concept used by the Google Earth engine. So when you, for example, process some, if you use Google Earth engine, sometimes, anytime you can perform, I don't know, some NDVI calculation for the whole world, but actually you are not processing a full resolution image. You are just processing a downscaled image. And even if you are working with Landsat data, it's just a downsampled version of that Landsat data, maybe to 1 kilometer, 5 kilometer, that it's that provides an overview for you. And when you zoom in the map, you are actually changing between these overviews. So, and as we are providing it using a file name convention and like date format here, you can play with this year. So I can get the other year here, just changing. So here it's the same URL. Because QuantGIS keep it for me, and that's nice. So, and you can see I'm just changing the year because the interval it's the same. So I have the same interval, it's summer in the context of the project. And we are accessing now, this data it's from 2011. And now I will access 2019. And again, I have an image without contrast, but now I will just copy the contrast from other image for the other image. So here, if you click with the right button of the mouse, you can copy style. And I will copy to here. Let's see if it will work. Okay, that's nice because it means that I have two images with the same range of values. What makes sense because we are harmonizing. We are using a product that it's harmonized, and this it's a very good example because this image it's mainly produced by Landsat 8. So the pixels here were collected by Landsat 8, and after a lot of pre-processing, because we are using a product derived from the produced by University of Maryland, we took these images and we did another level of processing and aggregated it by season. And here, at the end, we have a full coverage for the whole Europe for 2 different years that actually were accurate by different satellites. So it's pretty interesting. And let's zoom in here. I will disable it. And now you can compare. And yeah, the image it's harmonized, but you can see that the quality of 2019 it's better because Landsat 8 has a better sensor, and you can go to any place in Europe. So one thing that it's important is remember this is access to a real data, but here you are. QuantGIS, it's playing with these visualizations to provide a good and fast overview for us. But you have a lot of raster processing tools here in the QuantGIS. And I don't know, maybe you want to clip raster by extension, for example. So if you use, for example, if you provide the extension for this whole area here, like including multiple countries, like a big area, it will take a while, because to perform this operation, you need to work with the real data. So the QuantGIS will download it and really will clip this data for you, but it will generate a big image and probably the process will frozen. So this is nice, but you need to be aware that it's actually a proper service to access like parts of the data. So I will do something here. So I will just get this area here, and you can go to raster, clip raster by extent. And I hope it worked because I didn't test. So I will use my mappa canvas, and you can see I'm using the right projection. So all the metadata properties and everything was derived by this cloud optimized GeoTIFF. This is a remote file. It's hosted in our server. And this is actually the command that you can see with the GDAL. And at some point here, you can, probably I will do, I will enable this compression, compression. And let me just check this. So in the GDAL, so now I will use the GDAL, because actually QuantGIS, it's just generating a GDAL command for me. And yeah, compress. So here you can see all the compression algorithms that we were, that are available, and we talk about the LZ, LZW, and deflate. So I will use here compress, and I will put this one. And this is actually the command. So this window, it's just to generate this command. And you can see that it's using the vscure. It's a common URL access library, but GDAL, it's using it to access the file remotely. And it will provide the output here, and the output, it will be written in here. Yeah. Okay. And the important command here, parameter here, it's actually this one. So this is the window. So it's the extent of the area that I selected. So, and now I produced the local data. So now I have some local file here, and you can see it's possible to see because now the extent it's different, the colors are different. And I will use the same style. And okay, this is the local file. So what we did here, we accessed a remote file. We navigated across Europe and selected a specific area. And for this area, I downloaded like the data, and now I produce a local GeoTIFF. And you can see the location here. Now it's in my machine, but it's in the temp folder because QuantGIS managed it for me. Okay, this is nice, but it's not like doable. Do it for several images, thousands of images. So now we will use the notebook to actually do the same thing and a bit more. So I will go to here, and I will restart my kernel and clear outputs. So, and okay. And before I continue, I would like to show that it's important to update the repository because we are testing this code and do some changes and fix. So you need to open a terminal and it's ODSE workdir code, ODSE workshop, and this is a GitLab repository, and you need to do a git pull. It will bring some new files if you don't have yet. And for sure, for after the training session, we will add, for example, the presentation, so you can do like one last pull and get the whole content that we presented, including data and everything. So, and it's better to use it outside of the VirtualBox, but to practice, you can use the VirtualBox and do it later. So now we have the new version of the code, so it's updated. And if you click in the Jupyter Lab, you will see these files here. So I will just navigate to open the files that we have in the repository. So the ODSE workshop, Python training, and this working with cloud optimized geotiffs. Okay, and this is our notebook. So mainly here we will access different data because we will access the red band. So it's just one band. It's to demonstrate, but it's the same concept. So the RGB mosaic, it's 3 bands and it provides a color composition. But here it's just one band but it's the same concept. So let's start with the library. So here we are mainly importing the raster IO, NumPy. Yeah, it's better, right? Here, I will remove it here. Yeah. So, okay. And let's use the same code that we are using to do this repository definition. So our data is here, and we will use this as cog output. So the goal here is really access the data as we did in the QGIS, but now saving it like using Python, so programmatically. So we can really do it automatic and iterate over several images. So, but I would like to explain first these overviews. So if you, so this is the URL, so it's hosted in the same service. And here I'm just passing this URL to the raster IO. So, and here we are using actually the raster IO. You could use the read raster to read it, the UMap package, but raster IO provides some functionalities to access the data directly. So, and in this data here, we will get all the overviews. And I will show it to you, but most important, using these overviews, so that the pyramid layer, the parts of the data that were pre-processed and downscaled to provide a sort of visualization and a preview for us. It's not like the original data, but was pre-computed. We will use it to actually read the data using this function here. So I can define an output shape. So, and internally raster IO will understand that I'm trying to access just not the original data, but an overview of the data. And if you do it, you can see that here we have these levels of overview. And the last one is this, so the image will be rescaled like in this proportion. And actually, here I'm just getting the last overview, so the smallest one, and this is the size of the image. So it's actually like a pretty small image, just a thumbnail, but it provides me a good visualization for the Europe. So, and what it's nice here is the cloud optimized GeoTIFF, the format, manage it for you, but we pre-processed it. So it's why we have these overviews calculated. So if you generate a cloud optimized GeoTIFF using the GDAL, it will take more time than a regular GeoTIFF, but it will allow to the users really access this overview and have a thumbnail of the data. It doesn't matter if it's Word or it's the Europe. It's just a matter of to run, and it will pre-compute everything and prepare in a nice way to be consulted. And it's what we have here. But maybe this is too coarse, I don't know. But you can choose here a different overview level. So, and I will now get this one. So I will move 2 positions considering the end, and I will just print here. Oops. Here, okay. Oops. Yeah, I'm using the okay over. Oh. So you can see now I changed the overview, so now I'm using a different level of overview. It's not more the smallest small one, and now you can see that the image it's a bit bigger. And yeah, quality it's a bit better. And yeah, I can play with that, but of course, if I go to the level -8 or the first level, I will bring much more data, and it will take a lot of time because actually needs to download all the data. So, and what it's nice, for example, imagine here this is actually real pixels. It's why I can do this plot, but and here it's just like a NumPy shape. So we'll just print here. So, and of course it's starting with 0 because it's just this part of Europe, but it's a NumPy. So imagine you can calculate, if you have the red band, this level, this overview, and if you have the near band, you can calculate an NDVI in this little image, and you can see the result across the whole Europe and check some problems. Actually, it's how Google Earth Engine in Ensemble, actually. So you can do the same thing. And okay, so now what we will do is now we'll use this IPy leaflet to present this web map for us. So this is a nice plugin where you can put some different base layers. Actually, you can put the Google Maps here. You can insert some draw controls and some layer controls. And this is actually a interactive map, and you can zoom in and you can move around. So yeah, it's just a map, and you can it's a pity that you cannot plot directly the cloud optimized GeoTIFF. They are work on it. There are some libraries trying to do it also. Leaf left map, something like that. But maybe for sure in the future they will integrate this functionality. But now we are using this plugin here just to draw a rectangle. So it's just a regular geometry, and you can see that I have this draw control here, and I created it, and I just added to the map. And with this draw control, it's possible retrieve the bounding box. So here it's the bounding box that I created in the inside of this map. And now I will use this bounding box, and it's important to remember that I can see these projections are not the same one. The projection system, it's not the same one from the OpenDataScience Europe, so you need to convert them. So I'm doing it here. So I will convert from this WGS 84 to our projection system, and I will generate a proper window, a proper extent, and using this extent, I'm actually generating a window object. And this window object, it's just like a representation of a window over a projected raster. So here, this call off and this rule off, it's just like the offset considering the beginning of the image. And here it's the time, the size of the data that I will retrieve. So it's a nice system provided by raster.io. And now, you need to create it from your extent. And now what we will do is actually get the URL. So here's the data, red band. We will use this read raster, our function, to read this cloud optimized GeoTIFF. But as we did in QGIS, I will just send a window. It's possible to read the whole data. If I remove this spatial window, I will retrieve the whole data. But in the most part of the case, the users don't want to do it. You are just interested in some part of the whole data set. And now, if you execute it, it will get the data. And using this, so this is a NumPy array, as we are doing the last Python training sessions. And now you are plotting it. Here it's just a rescale of the values for between 0 and 1. And you are plotting it using these colors here. And you can see that it's the same region that we generated here. And this is a workflow that we created here just to enable the users to access like other specific region in Europe without go to the QGIS. So you can go to any other part and you can do the same thing. Now I think I'm in German. And you can draw a new window here. And if you see this function here, it will get the last geometry. So now I have two geometries in my object, and I can repeat the process. So now I have the extent, the window, and I will generate it again, and now I have other data. And this is just a NumPy array I'm accessing directly, and you can play with that now. And this is nice because imagine if you could go to the OpenDataScience Europe, you would download the data But you need to imagine that you have we are providing a nice functionality in the web viewer to download it. So you can clip, you can download it. And when you download, you need to save it. So you have the time to download, the time to save in the disk, and the time to load it again. And here, everything is happening on the fly. So actually, you don't have the download, you are downloading a file directly to the memory. So it's not necessary to write anything in the disk. And this is a nice advantage. And here, I just changed the, I don't know where this image, I will just put the test. And now I'm saving it in the disk, so I can save it. And you can optimize it and clip and get different parts of Europe automatically. And so how we are with the time?
30 minutes.
Okay. So now, and we did see it with the QGIS, but I'm using here the GDAL, and this exclamation point will inform to Jupyter Notebook to run a command like in a terminal mode. And you can see here that I'm using the GDAL to, and if you use directly the GDAL, you need to inform this first part here, this prefix before the URL. So, and with this URL here, it's the same one. And you use the GDAL and you have like all the parameters for this image. And here it's the original size. So it's a big image. And you can have it and you can see the projection system. This is the original one. And we did it in with QGIS. So, but here it's just an explanation of how to execute it by yourself. So you can send again a projection window and a projected window, and you can access the URL and save the output here. And so, and here it's just like a comparison, and it's comparing the two images that were produced by the Python and by the GDAL. So, okay. It's because I changed the bounding box, so I will not execute it. The image, maybe I will execute it just to show. So you can see that it's the input size. So it's a big image, but actually the GDAL knows. And this is the concept that I explained in the slides working here. So I have a big image, but it's not necessary to download it at all to access parts. So it's a kind of random access mechanism that allows to go specifically for each part of the rasters that I'm interested. And here you can see this is the tiling system. So this image, all these pixels here that we can see, so it's a big image. It's not just one chunk of data. Actually, it is split in different tiles, and each tile has like this regular size. So you are in the file disk, like in the when the file is saved in the disk, you have like a smart mechanism to access just these parts of these tiles, considering the way that it was prepared. And now because I changed the name, so I think it's test. Yeah, so you can see this is the file that I generated with Python. It's for some region in German, I think. And here is the file that I generated with the GDAL translate. And it has the same projection system, the same pixel size, of course. And the block is less than the tile system, but has less pixels, and because it is for different regions, these files. So till now we access this data, we clip it, we save it, and most important, it's possible access directly to the memory. But there is other type of analysis that might be interesting also, is because you need to remember that these files, the Landsat archive that we prepared here, they are really temporal data. So you have 84 images with this size for the whole Europe per each band and per each percentile. So you can have like a spectral, imagine that you can retrieve for 1 pixel, you can retrieve the pixel for the whole period and see like a time series. And it's what we will do here. But we also have an NDVI time series, so we will access it and actually see the result, because the NDVI, it's more easy to understand the signal. But you can do for any kind of temporal data that we have, even for the land cover. So you can use the same code to retrieve the same information that we are providing the website. You can get 1 pixel and see how the land cover changed across 20 years. But for the land cover, it's just 1 layer per year. With the Landsat and DVI, we have 4 layers per year. So it's more data. And we will use here the same concept, but as it is a time series analysis, you need to work with points. So I will get 1 point here. So in here, you can just put 1 point, put here in the vegetation. Maybe for this exercise, it's good to change to the Google images. And so actually, let's do it. Here in the leaflet, so base maps. So we are using this library, it's pretty nice. And I will change the base layer to a satellite image. So here you can see all the options that are available. So I think the best one is Hydra, Esri. Let's try this one. So you can just select my specific base layer here, and I will replace the original one, this one, Mapnik. Okay, this is better. So, and now I will go to, okay, not so better. Okay, so yeah, there is a limitation. There is a hazard layer there, but it's just to get a pixel in a vegetation here. So now I have a marker in some vegetation, some vegetated area. And here I'm using the same approach, but now it's a point. So it's not a rectangle anymore. And this is a WGS coordinate system. And I will use it to, again, convert to the projection system from the that we are using in the OpenDataScience Europe. And to do it, mainly I will open the cloud optimized GeoTIFF in the same way, but instead to retrieve a window I will just get the pixel value. So there is a nice functionality to a nice method inside of raster.io, do a sampling. So you need to send like a point, a coordinate in the same coordinate system of the image, and it will retrieve to you the pixel value. So yeah, so it's using this coordinate, the raster.io, it's going to the file hosted in the S3 and access just 1 pixel of this file. And this is the value that we are receiving. And here you can see I just changed the URL because now we are accessing NDVI data that were rescaled to 0, to a range between 0 and 255 to reduce the size of the file. And however, in this example, we need to access, the goal here, it's really access all the data. So we have a time series of NDVI ready to go in this service. So you just need to provide like all the URLs that you want to access. And here I'm using the same concept that we used till now, but now applied to the cloud. So I'm creating like a list of URLs that are sorted by time. So, and here you can see that I have this base URL, and here it's the position of the date field in my in the URL, and here are the dates that I want to access. And of course, you need to know these dates. And right now we are organizing the system to provide like a comprehensive catalog of all these layers. And I will talk about it in the end of my presentation. But we are putting this data and these dates specifically, but the data also the URLs in the documentation that we are organizing for the package and in the tutorials of the website. And you can see here that it's just a matter of to change the year and create all the URLs. And here it's an example with the URLs that we created. And now you can check how many URLs we have. So here is 80 because actually this is the old version of the NDVI. We don't have the 20 here, but we already processed it, but now we are updating the service. And you can see that here it's the version 1.0. So some of the tutorials you used the version 1.1. And now, using these URLs, we will create like we will send it to a function to do this access in parallel. So first thing, we have this read pixel function that will receive a URL, and create a coordinate and specific for a coordinate system. It will open the cloud optimized GeoTIFF using raster.io. It will send the coordinates and select and just retrieve the value and return it. But this is a function, so it's just a function definition. And here are the parameters. So, and now the parameters, it's just a list with two tuples. And you can access, you can see that this list has the name, the URL for the cloud optimized GeoTIFF, and the coordinates. And here are the coordinates. And of course, it's the same coordinates, but now we have a list of parameters. And what we are doing here, I will execute it. So we are using the parallel helper to call this function in parallel using all the cores that we have available and sending this 80, this list with 8 elements. So actually, here we are accessing in parallel the cloud optimized GeoTIFF files to retrieve the pixels, and we are putting this result together in a pandas data frame. And it's taken a while because now we are accessing all the files, but it's multiple files, but just a small part of the data, actually the smallest part of the data that it's a pixel. And you can see here, so it was not so bad. And now, so this code here do everything actually. So this actually, again, this is a parallel function that will call the read pixel. So, and read pixel, it's a function that read just one pixel for one image, considering coordinate list actually, could be more coordinates. So this is runs in parallel, considering all the URLs that we defined using all the cores. So if you have a eight cores, it will work using everything. And the result is actually like the pixel values here. And the rest of the code, it's just to prepare the data frame. So here we are, because we have the file, so I'm getting here the name, and I know the coordinates, and I'm getting putting the name of the file here, and as this file name, it provides like the start and the end date. We can put it as separate columns, so it's just a matter to split this file and create specific columns for it. I'm putting the longitude and latitude that I did consult, and here are the values. And so, and you can see it's one value per each image, and it was produced on the fly. So we did consult everything, and using this data frame, of course, we can plot as we like to see. Like this is a time series that we retrieve right now, but the values are weird for NDVI. So here I'm just rescaled the values, and you can see the variation here. And even for the Landsat, because it's difficult to produce a time series like that for Landsat because it's a 30-meter resolution. But it's nice because we have 4 pixels per year, and it's possible to capture part of the seasonality inside of each year. And sometimes there will be some problems for sure. Maybe there is for one specific year and season, the gap filling didn't work well, but in general, we have a nice product that it's ready to be accessed using all these different protocols and technology. So I will back to my presentation just to summarize. Yeah, this was the. Yeah, what you have here? Yeah, so. Yeah. So now we access so I presented how to access it in QGIS, how to access it in Python, but considering all the layers that we have available in the OpenDataScience Europe, we are developing a QGIS plugin specific to access this data through cloud optimized GeoTIFF. And the main advantage of this plugin, it will have it has actually, because all the available layers. So for example, you can check that the land cover is there, which Landsat data is there, and the NDVI, so you can play with dates here. But better than that, you can present it in the QGIS and see, like, in the same color scheme and the same style that we are using the OpenDataScience web viewer. So, for example, here is the land cover. I didn't load it in our previous example, but if you load the land cover data, it's nice. You can load in the QGIS, but you will have, I don't know, 33 classes, and just to select the colors, it will be a pain just to start checking the data. So we are providing the styles also, so that it's available in the Open Data, in the EUMAP repository. Actually, it's in the spatial layers. I will show it. But this plugin do all this work: access the data, get the style, and show it directly in QGIS. So, and it's under development, but I don't have the plugin here set up in my. You have it here? Oh, okay, you have it here. Okay, nice. So yeah, we have it. So that's not my machine. So let's see if it's working. So, okay, so you have a problem here. Yeah, we installed it, but we need to check the version. Okay. Yeah, I will just show the repository, but at the end, when we are really closing and finalizing the first version, but the plan it's really provided in the repositories of QGIS. So, but you can see that it will appear here, and you can select the layers. So, but for problem of dependency, it's not working properly here. But I would like to show the EUMAP. So here in the geo-harmonizer repository, you can see that it's the same group for the workshop repository. You can see this spatial layer, and here we are providing all the styles to open the data. So for example, if you load the QGIS layer, you can download the styles from here. And for the land cover, it works pretty well. And so, yeah, we are developing this plugin also. And so to close my presentation, I would like to talk about the stack. So we are working to set up it, because now if you think we are organize all this data and these raster files in a cloud optimized GeoTIFF and providing it as a cloud object service, but you need to enable the users to access this data. So it's a nice way to access, but it's important to provide like a kind of catalog with some metadata. So we have the geo network, but the geo network, it's not specifically for raster data, and it's more like specific for geospatial data. But the stack, it's a specification that provides this structure to put this data available in a proper catalog. And if you see here, you can see that the most part of these big players, they are using it. So you have data from Google Earth Engine here, Microsoft Planetary, I think. So you have Sentinel data. So this is actually, so you have the USGS. So these are public catalogs that can be accessed, and you can retrieve, like you can, first you can consult here and access the metadata and find specifically your image. And later you can get like a URL, as we are doing in the Python training session. And with this URL, you can actually access the data. So we are working to establish a stack server for OpenDataScience. And the goal is really improve the access to the data. And here are some catalogs that I presented. And yeah, as conclusion of this presentation, it's easy to claim that cloud optimized GeoTIFF, it's the state of the art standard to distribute data. So and if you use properly, it's like a geospatial database, but for raster. And for me, it's a nice combination of accessibility to the data, but also it provides a quick way to visualize it, because the most part of, I don't know, 30–40% of the work with raster data, it's visualize the data. So if you just provide access to an abstract array, and you can see, for example, the data, it's for me, it's not a proper way to work with raster data. And so the overview and these pyramid layers structure are really like good and fits really well in a workflow for who works with the geospatial data. But on top of it, we are aware that we need to create a stack catalog and provide this data also like with some sort of metadata and some, we need to improve the way to access these URLs, because right now it's in our GitLab, and Stack, it's the right way to do it. And yeah, that's my last slide, and that's all that I have to present. Let me see here. I'm trying to find Zoom. No. Yeah, sure.
Can you construct time series for multiple points?
Yes, it's possible. That's a nice question. So the question was if it's possible construct a time series for multiple points. Yes, you can see here that this is the function, and this function, it works with multiple points. So we can try do a risk test here, but let's see. So, but I don't know if the data structure here, it will work. Because if you have multiple points, the structure here, it will be a bit different. So this code needs to be changed, but the most important is this here. So actually you can send multiple coordinates, because this data source sample, it accesses the GeoTIFF file, but if you have a list of coordinates, it will retrieve the both values. But it needs to be changed here in the code. Maybe we could test with just one point here and see. offset here.
No, because you have that, yeah.
List, right? Here maybe my offset was not. Yeah. So here you can see this function. I'm calling for 2 points. This point it's just a offset, and now I have 2 values. But to produce the time series as we have here, we need to change this code, because this table, for me, the right way to create this table is actually expand the number of lines, right? So you can, if I send 2 coordinates, I would have like 106 lines. So it's possible. Let's see if I have. Okay, let's check the chat. All right. So no more questions, and we are on the time. Thank you for the attention. And we have one more session today. And thank you.
Can you hear me? Can you hear me? Okay. I can hear you. Just a moment, I can hear you. I cannot hear you, just a sec. Valentina, can we test again? Maybe I can hear you now. Again, I cannot hear you. Just. Kako nam bija še, Alex, se za full screen? Neće. Ok, nema se.
Smet onda. Meni je to ovako. Jesi to htjeli ili?
Ne, vrati.
F11.
This meeting is being recorded.
Okay. So I have problem to hear you, but I hope that you can see my screen. So I don't know, maybe only chat is possible to see if everything is okay.
Inputs. Can you hear us now?
Yes, I can hear you now.
Right.
So good. So you can see my presentation?
Yes.
Oh, good, very good. So, good afternoon. I'm Milan Kilibarda from Belgrade. I'm here associate professor from Faculty of Civil Engineering on the Department of Geodesy and Geoinformatics. I'm sorry that I'm not there in Wageningen. I was in Wageningen when I was doing my PhD and I had very nice time there. So I hope next time for the next workshop, we are going to see each other live there. I'm also head of the laboratory for development of the open source geospatial technologies in Belgrade, and also I am co-founder of GLab company. So I will say a few words about the laboratory and about the company. So the main aim of laboratory is to promote open source geospatial technologies in education, research, and in the industry. We are experienced in Horizon projects. We had 2 projects. Apollo was the first one, ended 2019, and it was advisory platform for small farms based on Earth observation. The second Horizon project that we are still running at the faculty is Beacon, and it's also related to application of Earth observation in agriculture, especially in agricultural insurance. And besides the Earth observation data and meteorological data, we also use in that project blockchain technology for the smart contracts and similar. So if you want to see more about the project, I share the link and you can explore more. And another also ongoing project at our laboratory is CERES, and my colleague, Professor Branislav Bajat, is going to present CERES and results from CERES that we have so far. And it is also related to the agriculture and application of Earth observation data, but in combination of a lot of machine learning and aiming also to help in field of smarter, or let's say regenerative agriculture. At the company, GILAB or GLab, Geoinformatics Laboratory, we are mostly dealing again with Earth observation data and very frequently use of Earth observation data in agriculture. But we also developed a lot of web mapping applications, and we have also our product, Crop Lab. It is a platform that help and support agriculture based on Earth observation data, mostly remote sensing data, including Sentinel-1 and Sentinel-2, and other in situ data to support, let's say, smart agriculture. We are also involved in the development of OpenLandMap application and the web services related to OpenLandMap application. We are developing geo-harmonizer app and the web services related to geo-harmonizer. I saw today you were using web services for OpenDataScience Europe portal. You were using also GeoNetwork services and GeoServer. And I guess that you had time to explore maps OpenDataScience. And I think during this presentation, we are going to explore more web mapping application related to OpenDataScience. We also were doing land cover mapping for Serbia, Denmark, and other projects. We have also project Dion, that is ongoing project, and we are coordinating AgriCapture project. It is going to be described also on Thursday, maybe by myself or my colleague Dragutin, who is co-founder of GILAB, is going to give a talk related to AgriCapture. So that was shortly about me and the institution that I come from. So today we are going to speak about the web mapping. We are going to say something about terminology related to web mapping. We will see what was the most important moments in the web mapping history. We will see also evolution of web mapping, and we will discuss, or we are going to see one of the vision of the future of web mapping apps. After that part, we are going to talk more about web mapping services. And I saw that today also Martin Landa was explaining web mapping services a lot, and you were exploring web mapping services in Python. But for this presentation and this workshop, we are going mostly to use just web browser, and we are going to try some examples in QGIS. So for the examples in QGIS, it is only necessary that you install plugin QGIS to web, and everything else we are going just to explore in pure QGIS. So if we are talking about the web mapping, there are different definitions of web mapping, but let's revisit the definition of cartography and web cartography, and then we are going to see what is web mapping and what is the term that we are going to use in this presentation. So if we remember, cartography is scientific discipline which study methods of producing and ways of using maps. So if we go to web cartography, we can say that it's very similar to typical cartography, but it has only, let's say, the difference of way of medium of dissemination, because medium of dissemination for web cartography are not papers or just screens, it's a web. But when we talking about the web mappings, we mostly think about the technologies of design, implementation, and dissemination of maps on the web. But we are not going to talk in this presentation only about the maps. We are also going to talk about the, let's say, web mapping services, not limited only to cartographic representation of the spatial data. And if we if we remember what is the definition of the map, so we can see that map is abstract. We can say that map is abstraction and selection of geographic reality with clearly highlighted spatial shapes and relations. But when we have web map and web GIS applications, there are also new roles of the maps. So you know, even if you are not from the field related to the spatial data, that maps can be a part of search engines, can be interface for other multimedia, non-geographic data, and can be used for collaborative mapping, and many more functions are now available on the for web maps. Also, there is a lot of web map applications that are used in everyday life. So let's say I think I saw somewhere that 1 billion people use Google Maps at the daily level. But so when we say that web mapping is let's say studies part of cartography, or let's say part of GIS science, that dealing with maps on the web, it's very important to see what was the evolution of the web, and to see how it influenced evolution of web mapping. So let's say that we can define web as a tool used by billions of people to share, read, and write information, and also to interact with other people via internet or via global network. In the evolution of the web, there are, let's say, three eras in the webs: Web 1.0, Web 2.0, Web 3.0. Some authors, they provide also Web 4.0 and even Web 5.0, but let's say that this evolution is quite enough to understand the key pillars of those eras. The Web 1.0, we can also call it synthetic web, or we can call it read-only web, because mostly in the web application websites that were presented in that era, consumer of the web page was only the reader. So example of that websites are, for example, personal sites that only shares the information about some person and some use of some person. And after that, we have Web 2.0 that we can call also social web, or we can see it as a read and write web. So the most important part of this era or epoch was that the user become creator of the content. So typical examples of these epoch, this era is, for example, YouTube or Wiki and similar stuff. And technologies that involved in this part of, in this epoch was HTML, JavaScript, and frameworks like Angular, Vue, React, and similar. And on the end, let's say the current epoch started maybe a few years ago, is Web 3.0 or semantic web, where we can imagine also that part, and we can think about that part like read, write, and execute. But also it can be understand that we are trying now to have a web application that and a web that can read and interact with the content. So web page or software cannot really understand the content, but based on the semantic organization of the data, and by using artificial intelligence and machine learning, it can provide some very useful information to the user in a way that it's similar like that web application understand the content on of the web page. If we see technology related to web 1.0, we can see that we have in this left part that data are mostly structured in a relational database. On a server, we have dedicated server, and the internet is mostly available on, using wire, and we have a desktop browser as a medium for consuming web page and web applications. On the web 2.0, we have big data. We have also we have cloud computing in the as a middleware, and we have mobile phones and the browsers and similar devices to consume the content of the web. On the web 3.0, we are going to have many things that are related to artificial intelligence, distributed computing, Internet of Things, and stuff like that. If we go further, we can see also significant events in the web mapping history. And we can say that the first event was first web map created in 1993. After that, map server was realized, and we have many other intermediate events. In the year 2001, GeoServer was realized, and later on OpenStreetMap was founded in 2004, Google Maps in 2005, and stuff like that. So we will go through these events in the further slides, but let's recall the paper from Venedal and co-authors about reviewing web mapping eras. So the next 10 slides are mostly focused about the findings that they provided about the web mapping eras. So related to web mapping eras, we can say, or Venedal et al., they divided it in 9 groups. And these nine groups, starting from static web mapping era and finally going to the end to intelligent web mapping era. So when we're talking about this era, we do not think that this era started and it's finished. So there is no end for many of this era. For example, service era that we are going to explore the most later on, started around 2000, but it is still alive and still very important for many web map applications. And this on this picture also you can see the stars, and the star indicated the approximate start of the development in that era. So the first era is static web mapping era. It is fully web 1.0, where we had that maps were HTML image. So we do not have, let's say, almost any interaction with the map. And the first web map was Xerox Spark Map Viewer, made in 1993. But if you remember, I can remember, in 1993, I was 10 years old. For example, in Yugoslavia, most of us didn't have even PC, and you can imagine how how internet was limited in that time in Yugoslavia. So pioneer of web mapping was Steve Putz, who made Xerox Spark Viewer in 1993. So in that viewer, the interaction was possible. For example, if you want to zoom, you had 4 options to zoom out and 5 options to zoom in. And on the click on zoom, you have change of image. So let's say it's I think only this and the next era is era that are not evolving anymore. After the static web mapping era, we came to dynamic web mapping era. So dynamic web mapping era included technologies that were capable to dynamically create and construct the maps requested by user on the server application. So in that period, we have client-server architecture, and we have some software that were capable to produce maps on the request from user, and also dynamically changing zoom, pan, and stuff like that. It changed the request. It sent a request to the server. Server draw the map for the user and send it back to the user. And in that period, we have 2 very important applications in the evolution of web mapping. The one is Canadian Atlas, and another one is National Geospatial Data Clearinghouse from United States Geological Survey. So it was very important era related to the evolution of web mapping, because it showed that it's possible to have services on the server side. And it made the idea that map server application should be standardized and should provide interface to the client and to the any users on the standardized way, and that that content, map content, can be used in different applications, in different client applications, not depending on the implementation on the server side. So in this architecture, where we have client-server interaction based on request from the client, server consume request, draw the map, and send back the results to the client, we have first development of services, and not only clients from the web browser, let's say typical users of the web apps, were capable to using web mapping, geospatial information from the server, Also, it was starting of use geospatial information served from the servers in other applications and in a different type of clients. So very important, as I mentioned before, was developments of standard and specification by ODSE, implementation of that standards, for example, in map server and GeoServer and similar. And there also was beginning of clients API, mostly JavaScript APIs like OpenLayers, Google Maps API, Leaflet, and similar. So let's say this era is actually very popular right now also because many of web mapping applications still rely on this technology. We have also era that is connected very to the previous one, and it is let's call it interactive web mapping era. And this era is the main difference between this era and previous one was Ajax, because technology that uses asynchronous JavaScript and XML made possible simultaneous interaction between client and server. So in the previous era, it wasn't possible, for example, to update web page without reloading the old page. But in this era, so you can see web application as a part of elements, and each element can request data from a server after the page has reloaded, and consume back the response from the server, and to only to upload that element of the web page. So it was very important part also in web mapping, not only in the web applications. And for this era, it's typically was that mashups showed up the first time. And in that time, you had mostly Google Maps API mashups and a lot of maps created on that technology, based on that API's technology that combine user data together with data provided from some provider, in this case, for example, from Google Maps and similar. After that, we have era that we call it, that Vanidal et al. Call it collaborative web mapping era. And it is also typical and related to appearance of Web 2.0, as it was popular for any other web apps like social networks, YouTube, Wiki, and similar. It was also very important for the web mapping era because OpenStreetMap was founded in 2004, and we have the first time crowdsourcing collaborative mapping, and it was started just for the United Kingdom, but as you know, it spread rapidly across the world, and we now have a very good web mapping application based on crowdsourcing, and we have available, let's say, great details of spatial data that are free to use and share, create, that are free to use under the ODBL license. So you can create, you can share, create, and adapt the database as long as the share alike is keeping as attribution to the data. After that, we have an era related to digital globe, and we have a few examples started from the commercial companies like Google Earth, and after that Microsoft Virtual Earth, now Bing. But we also have virtual globes available as open source like Cesium and NASA Worldwind. You know that digital globe or virtual Earth is a virtual representation of the Earth, and it can display different views of the planet, also natural and human phenomena. In this case, you can see the building of the Faculty of Civil Engineering. So in that also in that era started to be important display of 3D objects. KML involved after that CTGML and similar. Also in Google Earth, I think for the first time a representation of spatiotemporal data was much better than before, including animation and similar stuff. After that, we have era that, of course, is still alive and still very important, and we can call it mobile and location-based web mapping era. So in a period when different devices were popular and with operating system that can handle with complicated apps. So we have tablets, smartphones, and stuff. Web maps were popular to. It was popular to build web mapping applications for the small devices and small screens. With evolution of GPS technology and the possibility that we have GPS enabled in smartphones, it was beginning of development of location-based services. So now we have a location from the smartphone, for example, and we have a service that depends on location at that moment, and data and services related to location were available to the end users. So you know, most of you are using these services. For example, if you use Google Maps for routing and similar applications that can be very important, for example, for marketing, for the navigation, for even for playing games. If you remember, Pokemon started based on this location-based web mapping era. And in this era, we have also important thing that it started to be used in very, very frequently, and it is Internet of Things, because in that era also started that we have a lot of devices that can handle location and that can in the same time be a sensor for surveying and getting the data for many aspects of life. After this mobile location-based era, we have a cloud mapping era. So as you know, many popular cloud providers are also specialized for the spatial services. For example, Amazon Web Services, Google Earth Engine, and similar. So we have not only data as a service, but we have almost everything as a service. We have example for this era, GMap from Python package that can interact with Google Earth Engine data and services for analytics and visualization. In this era, we cannot say that we have so much open source solutions at the moment. Some can say that GeoNode is trying to be a web GIS solution that can be deployed in cloud and that can not only serve the data, but also to serve the services related to the data implemented in GeoNode. But still, I do not see the really open source solutions in this cloud era. And on the end, we have an intelligent era that, let's say, is started now and that trying to consume Web 3.0 as much as possible. So now we have big data, remote sensing data, Internet of Things, and a lot of data from different kind of sensors. And we have typical services, but we are trying now to make also the machine learning and the artificial intelligence, let's say, decision support system that are going to consume as much as possible spatial data and trying to provide content to the end user based on the experience from the machine learning systems and artificial intelligence systems. So in this era, we also know that it's mostly based on the cloud era because consuming this big data and computing effort needed for artificial intelligence and machine learning is quite a big issue related to big data. On the end, we have vision of the spatial web, or let's say vision of the future web apps. And if we have these three layers on this picture, we can see the first one, let's say physical layer or real world. And as we have before, we can make abstraction of this digital world by using geospatial models and geospatial data, even 3D data and stuff like that. But let's say like in civil engineering, like in construction industry, you now have the buildings and building information models that can also include sensors in the geospatial abstraction of the object. So in this next stage, most probably we are not going to have only geospatial abstraction represented as a 3D data. We are going to have also sensors data that sensing everything what is necessary related to that objects. So the third layer will not include only spatial data, but let's say spatiotemporal state of some phenomena that is modeled. For example, spatiotemporal state of the building in some moment that can tell you what is the electricity consumption in that moment, what was the day before, and maybe based on machine learning and artificial intelligence, what is going to be expected tomorrow and few days after that. Similar to that, the sensing can be also integrated with trees and with greens and with almost everything. And what is some vision that in this future era, we are not going to interact typically like we interacted with let's say, click on the desktop or in touch screen by touching the touch screen. Maybe we are going to use some smart glasses or voice command or stuff like that. And maybe the application will be capable to give you answer based on the based on speech, because maybe it is going to be possible that a machine can interpret your voice command and understand what is the most relevant that is going to be provided to you back. So this is one of the vision of spatial web, and this is, let's say, I can imagine that in next 10 years we are going to have something. We are going to have something similar like this. So it was, let's say, not so short history about the evolution of web mapping and evolution of web. And now we are going to focus on the, let's say, service web mapping era. As I told before, service web mapping era is still very alive, and many of applications interact with the web mapping services, and not only web mapping application, also desktop applications, and also as you explored today with the previous presenters, you saw that you can consume web mapping services in a different programming language like Python and R, and also in a different desktop application like QGIS, or you can use web mapping application to produce web mapping services to produce web mapping applications. So typical architecture of web mapping application is composed of these three important parts. So we have to have a web server, we have to have web map server, and we have to have web map client. So typically we have web server that represent a computer which has appropriate software, for example, Apache or Apache installed, and this software is capable to understand requests from the client and to send back information that was requested from the client. It is similar, like we have to have a web server, that we have to have web map server, which represents software that is capable to receive and respond to requests for geoinformations. So typical representation of geospatial server is, for example, map server or geo server or something of commercial like QGIS, or it can be also QGIS cloud server and stuff. On the third part, so you have web clients, and in the web mapping application, it is typically JavaScript libraries, which enables visualization, manipulation, and analysis of geospatial data by using web standards. It's not restricted to web standards, but it's most common situation that you have application that consumes standard web mapping services on the end. If we see just a moment. If we see the schema of web mapping services, it goes like this. User use web application, user requests something from the web server. On the web server, we have implemented web mapping server that is capable to deal with spatial data based on the request. Web server returns to the user browser geoinformation requested from the user. And the web client is capable to interpret and present that information, geoinformation, to the user on the end. So if we talking about the application that you were exploring today mostly and days before, maps.opendatascience.eu. I will show you the schema of the application, geo-harmonizer application, OpenDataScience EU application. So it's not, let's say it's simplified architecture, but in this architecture we have three layers. We have data layer, where are all the data. Some data in PostGIS, it's vector data related to Lucas. Some data are in cloud optimized GeoTIFF, as you saw before. Leandro and colleagues, they explained the use of cloud optimized GeoTIFF a lot. And some of data are only metadata, so data that can explain us what do we have in this application and in these services. So for the implementation of metadata, we use GeoNetwork, and all metadata are available on GeoNetwork OpenDataScience.eu. Also, we have web services implemented by using GeoServer, very popular web mapping server on the middleware, and we have REST API implementing in Python Django framework for querying the spatiotemporal querying the raster data. In this application, you also have in these services, you also have possibility to access REST API services and to access as well as GeoNetwork and the GeoServer. So in the examples later, we are going to see and access to some layers from GeoServer. It is the middleware, and it is, let's say, lays on the server component. And on the client component, we have the main part of the application is OpenLayers, that is a web mapping client that can consume web services from GeoServer and that can present you, like end users, maps and stuff related to the geospatial data from OpenDataScience Europe. Also on the front end, on the application that you see when you go to maps.opendatascience.eu, we have a React framework that is used to building this web mapping app. So the very important part of this architecture and architecture for many of web mapping applications is GeoServer, which implements ODSE services. So you also had today explanation what is ODSE. I saw the presentation from Martin Landa. I can repeat a little bit, and it is going to be some repetition from this part of presentation like you had before. But let's go slightly to the web mapping services. Very important moment in the history of web mapping was implementations of standards. And standards that are very important are OGC web services. OGC stands for Open Geospatial Consortium, and it is international industrial consortium with more than 500 companies, government agencies, universities, and other organizations that support interoperability solutions, including spatial data. For us, it's the most important is interoperability in spatial data. And what does it mean in reality? So in reality, it means that if you have implemented web mapping services that you want to expose to client or to other application like QGIS and stuff, and if it supports OGC services like standardized services, I don't need to care about your implementation on your server side. I can just consume the data that are exposed and provided from your server. So any type of client and any type of, let's say, desktop GIS application that can consume standardized services, doesn't matter about your implementation of web mapping services. So it's very important that you implement web mapping services in standardized way, because in that case you provide use of that geospatial data as much as possible. And some of the important web mapping services that we are going to show here is WMS, WCS, WFS, and stuff like that. So when we are talking about the web map service, we can say that it's a standard protocol for servicing georeferenced raster images. But you shouldn't mix it with the source raster data. So WMS deliver styled spatial layers. So it is just images ready to be shown to you in some web mapping application, or let's say just background maps if you are going to use it in QGIS or other GIS applications. So it's not served geospatial data, it's served PNG, for example, images to be ready for viewing. So let's say WMS services provides data that are ready to be consumed as a map, as a typical map that you had before. So WMS had several implementations, and the first one was in April 2000, and the last one that I know is 1.3. And what is the important to know that not each implementation is same in the way of requesting data. So it is the first one can provide some different parameters related to the request that you can send if you compare to the last one. So we will see some examples. So the first and the, let's say the simplest example is to ask server about the capabilities. And what we have, if we, like a client, ask server about the WMS capabilities, we have that we are going to have a list of available layers and some other informations related to the layers that can be consumed from that web mapping service. If we see another very important WMS request, it is get map. Get map returns raster image depending on parameters what we requested. So if we try to see example related to get capabilities, if we try to see example, we are going to have a big XML file that will provide us a list of all available layers, maybe some abstract about the web server and some contact person, and will also provide a list of coordinate reference systems that can be used from this web mapping services and stuff like that. So if you want, you can click on this and see what we are going to get. Before that, we should say that on the first part, we have address to the service. Then we have question mark. Then we have service that we want to see description for. And then we have ampersand related to other parameters we request. So this sign end version is 1.30 and request is gap capabilities. If we try to see, we have this WMS from our laboratory, and we have some contact points here. We have a list of available raster format that we can use for the get map. We have also here address to the WMS. And then after that, we have a list of all supported projections. And this is a very big list because we're not restricted projections to few. We have everything that is implemented in a GeoServer. And then later on, we have some basic description of the layers that are served here. So we have a bounding box of the layer, we have a name of the layer and stuff like that. If we go back, and we can see that this XML is not so easy to read. It's aimed to be human readable, but the main point of XML is that it supports that be also machine readable. So implementation of many clients support get capabilities to be much easier. So for example, if we try get capabilities for OpenDataScience EU, the request is going to be the same like the previous one, but address to the server and to address to the WMS is different. So we have this address for the WMS, and we have this service is the same. We will try WMS, and we are going to use to ask for the 1.3, and the request is get capabilities. If we click here, you will see GeoServer that provide to you these web services. And here on the layer preview, you will see the list of all available layers in this GeoServer. So if you click again on this, you will get this big XML describing all the layers available in the this web server, and you are going also to see the layer names and some bounding box and some basic information related to the each layer implemented in this GeoServer. But there is also easy way to explore this get capabilities from QGIS. So I also saw that you tried today with Martin these connections to the WMS, and it is easy in QGIS. So you go to the add layer, add WMS layer. You need to set some connection parameters like name of the service that you want and just URL to the service. to WMS service, and then you are going to have list of all layers that can be then loaded and can be seen QGIS. I don't know if I open QGIS, can you see the screen, or you can see only the Google Chrome? But never mind, so it's easy. Another important.
Hi, Kelly. We can see your screen, so we saw you open the QuantGIS.
Okay. So so I can add layers, add WMS. I have this parameter set it here, so I have name of this geo server is called ODS, and I have this address to WMS, and I can now connect to the geo server and to see the list of all available layers in QGIS. So it is practically similar, very similar to get capabilities, but now you have, let's say, easy to read the list of all layers and relevant information related to that list. Okay. If we go, let's say we can also add one layer. I will add this digital terrain model. And actually what we did now, we execute another request that we are going to show. It is request called getMap. So now we have a digital elevation model for Europe provided from.
We only see a slide. WMS getMap example. We only see the slide.
You do not see QGIS.
No. We saw it before. Now we see the slide again only. Maybe share again.
Okay, just a moment.
Yeah, now we see it again. Yeah, we see it.
So now what I did, I actually executed next example that I'm going to show. It is getMap. So we are now seeing a map of digital elevation model of Europe provided from OpenDataScience. And if we go back to the slides, what is in the background? So in the background, we have several lines. Now it's decomposed just to see it's easier. So the first, we have WMS address. The second, we have service and the specification of a version. Then we have a get map query. Then we have also, again, requested parameter related to the name of the layer that we want to see, boundary box. We have display size in pixels and display format. So if we compose it in one line, we have URL that can be executed even in browser. And if I execute this URL in browser, I'm going to get this map that you see on the slide. So you can try it also. But let's go to the example that we have. So if I want to see this layer, but let's say that I want to see the layer here in somewhere around Serbia, then I need to give address to the geo server to give what service I'm going to use, what version. Request is get map, and the layers, I took this one. So it is the same one that you saw in QGIS. But I also defined boundary box, and boundary box is somewhere like Serbia. And I'm going to have this I'm going to have something like this. This was previous one. So if I want to change the coordinate reference system and to be strict that I'm going to use longitude, latitude, WMS, longitude, latitude, VGS 84, I have to specify the coordinate reference system, but in this case, boundary box is different because in this case, I firstly have to give north, then east, then again north, then east. So the implementations of WMS in different versions can be slightly different. If we want to explore more, there is a list of parameters that we can use and that we can specify in request when we want to consume get map request. If we go back to QGIS, we can also give some background maps. So for example, we can use OpenStreetMap as a background or some Google Streets as a background and different one. So it is also some kind of tiling, web map services that you can add to the QGIS and use it as a background. So for example, if I go to XYZ tiles here, I can add some of the backgrounds directly. So I gave here in the slide a list of backgrounds that you can use in your QGIS as a background. If we go to explore, this it's simple. So it's similar like you added the WMS. You can define name of the background that you are going to use, and here XYZ link to the service. So in this case, we made this as a background. So if you go here and we make transparency to this layer, we can make, for example, even some traditional map by using WMS and by using QGIS and some other web mapping services. So if I go to new print layout, for example, and if I add this here, so I have practically WMS integrated in my typical standard map. So I can add something like, I don't know, I can add grids and stuff like that, and to make it like very typical map that you can see like printed map and stuff like that. For example, if I add coordinates and stuff like that. So let's say that we have created some map, we can of course add title and similar stuff here, and we can export it as a PDF or similar. Let's go back to the slides. Maybe if you want to try to add the legend, let's go here and try to add legend. You will have something that you maybe don't like. So there is also other option how to do it directly by using web mapping services. So let's say that we don't like this kind of legend, but we are going to explore it later on. So if we construct a get graphic example, so it is WMS request that can request from the service that we take a legend. We can have this like this, and now I can add it to QGIS. If I add a picture, and here I can say image. Okay, now I can download this image and upload here directly. But there is also option that you in some new QGIS you can just paste URL here, and you are going to have legend there. So it is something like this. So you can add legend, and if you define here picture raster image, you can just paste this URL from get legend request. Now we can try also to see how to make a simple web map by using QGIS and by using WMS layer. So if we are again in QGIS, we can close this. We can use the plugin called QGIS to web. And if we go create web map, I have here a list of layers that are going to be created by using this tool. So I'm going to also use the digital elevation model, and I'm also going to use OpenStreetMap as a background. I can use open layers as a client for web map to be created by using open layers library. And here I can set some additional tools related to the web map. Here I can say where it is going to be exported in some folder, or it is going to be directly sent to some server using FTP. And if I export this, I have simple web map here containing WMS and OpenStreetMap as a background. So if I go to the folder, I can see here is simple application that created this web map. If I go in layers, I can see implementation of WMS in Open Layers library. I have it here, I think, yes. So, just a moment. It's maybe better from Visual Studio Code. So here I have this get map from that we explored before, how it is implemented in Open Layers. So we have similar parameters that we can also define in URL, and it is quite similar that you have today with Python, that you tried and explored some web mapping services using Python. So this is the implementation, this is the code. So beside these two, the main request related to the WMS, we have also get feature info, describe layer, get legend graphic that we explored, and if we go back to the QGIS, and if we try to make info on some location, it is implemented in the background. So we have get feature info run in background, and we have information for any specific location about the, in this case, about the digital elevation, about the heights, yeah. But I think this is in decimeters. It's not in meters, I think.
Yes, you need to get meters.
Yeah.
I made the data, so I know.
So the next service that we can explain a little bit is a web feature service. And I know also that you work today with web feature service. So it's a protocol that enables downloading and editing data over the internet. And if we have a web feature service transaction, that's possible to use that service also for creating new, deleting, and modifying the vector data over the internet. Typically, when you use download from web feature services, the default is GML format, but you can also use S3 shape, JSON, and others. Mostly in the web apps, it's JSON and GeoJSON is consumed a lot. So related to the web feature service queries, we have get capabilities, describe type, get feature, and similar. So we are not going to go into detail because I see that we have 10 minutes more. But let's see how it is work get feature service. So very similar like that we have with get map service. So we have address to the web feature service. We have service name and version. Request is get feature. Type name is the name of the layer that we are going to consume. And here is defined that max features is 2, because I just wanted to see that we are seeing source data. So web feature service provides us source data. So we have coordinates and all attributes and everything necessary to play with this source data. If we take get feature service from the OpenDataScience Europe, here is one example. So we use version 2.0, and we have requested JSON format as an output, and we defined here that this ellipsoidal coordinates, and also we defined max feature. But in this version of 2.0, max feature is not defined by keyword max feature. Now it's defined by word count. So if you see the outputs, you see that we can use different formats. And if you try to add this web feature services in QGIS, you can get the data directly. And of course, you can use right click and save it like a geo package or S3 shape file or whatever. But please do not use this data directly, because here we have more than 5 million Lucas points. land cover points in this data set. So it's maybe not so clever to download, to consume all 5 million points in QGIS. But if you want to use selection by boundary box, you can send request like this one. So you ask for the data and you define boundary box as a limit for the data that you are going to use in some other application. For example, if I download this data in shape file format, it is going to be zip that we need to extract and then to add in QGIS. We cannot, for example, make a web map using these 3 layers that we had before, vector data, WMS, and tiling layer of OpenStreetMap on the background. And by using QGIS to web, we can make web map of those 3 layers. Next services that we should mention is web coverage services. If we say that web feature services is the downloading service for the vector data, we can say that web coverage services is the same but for raster data. If you want to take source pure raster data from the service, you have to use web coverage services. There are 3 main functionalities: get capabilities, very similar like we had before, describe coverage, and get coverage. So here I gave one example to get coverage where I use our laboratory server, and we are going to have this data in GeoTIFF. If we click on it, it is going just to download this data set. For OpenDataScience Europe, web coverage services are restricted. But you had today a lot of presentation related to cloud optimized TIFF and Wasabi that provides that data sets directly. And on the end, we have to mention web processing services, but I also saw today that you have example of web processing services provided by Martin Landa, and I think that we do not need to repeat again what is going on, because I would like also to show you the map Open Data Science application, because as I told you, GitLab team made this application. So here you have application, you have a list of background layers that you can use. For example, this one or big map. Then you have list of layers that you can also use to see the results. If I go here and click, I have also information about the attributes for this specific location. So I have this for chlorine land cover for these 4 years. What was the class here at this particular place? So I can turn off and turn on uncertainty and training points. For the training points, I have to be zoom in a lot because it consumes that WFS that I show you that have 5 million points. So here now you can see in the background it is WFS service that provide to you spatial data, spatial vector data, and attribute information related to this spatial data. If I go back, here we have some functionalities related to the legend, so you can see the colors. If you go to 3D, you are going to see a virtual globe implemented in cesium. So you are going, you have possibility to see this in globe environment. If we go here, here we have link to metadata catalog implemented in GeoNetwork. So if I click here, I have metadata for this specific layer that is now active. If I click here, I have access to Wasabi to download the current layer. I can also here, I can go and see animation for this layer and stuff like that. So I think animation is much better at this in 2D than in 3D. And I think we are on the time, so that's it.
Okay, thank you. Thank you. That was really thorough and really run through all the services and all the software that you use and standards. And we have some questions for you. So I will look if there's some questions in the chat. Otherwise, I have a question for you. So imagine like this. Imagine you are organization producing spatial data, let's say for whole of Europe. And let's say its organization is a low budget. And so this organization would like to provide access not only to view the data, but also for people to query the data. So like, let's say this web coverage service type. And so what do you think, what is the best option? What would you recommend today? What is the best option for organizations that would like to produce open data and provide it, let's say, with the lowest possible cost to highest possible number of users? What would you recommend?
So if we are talking about the vector data, I didn't mention that WFS 3.0 is going to be quite sophisticated, and it is going to be implemented similar like REST APIs. So it is going to be easy to use to even query the spatial data over the web related to the vector data. But related to the raster data, I don't know I think the easiest solution is cloud optimized GeoTIFF.
And for the vector data, like, I mean, how do people start? Like they install their own geo server, they get like on Amazon server or something and instance, and then they install the geo server, and then they put the data in geo server, and then they just describe what do you recommend? Which are the best steps? Is it better to make your own instance, or is it better to outsource or to, upload to some third party? What do you recommend to people that are now following this, let's say, listening, and they produce data, but they don't know how to publish data? What would you recommend?
I don't know. It seems to me that it would be the easiest if there is some institution that is willing to share infrastructure like their infrastructure, like their geo server and stuff, or their databases. So, for example, if OpenLandMap is the kind of initiative that you can share the data using that infrastructure, it would be the easiest. Implementing your geo server is not so easy, I think, but it's not also so much complicated. And cloud services would be also a very good option. So I don't know. It seems to me that something like cloud optimized TIFF should be also available for vector data. And I think that there are some initiatives that it's going to be developed maybe in years or two. And in that case, it would be the easiest way that use it like the same way like you use with cloud optimized GeoTIFF.
Mhm. Okay. Do we have other questions, audience? Questions? Leandro? So one question I want to ask you. In the Open Data Science Europe we noticed you did very good job with the GeoServer, and we noticed that animation is very fast. So when you scroll, as long as you have a good bandwidth, you can scroll very quickly. And so what's the magic? Can you just tell us how do you get such a good system?
I don't know. It is mostly experience because we worked with this kind of projects a lot, and let's say experience of setting everything to work smoothly is the key thing.
But usually it's also setting the parameters like the cache size, adding a lot of RAM to server, using the SSD, right? So
Yes.
there are a couple of technical steps. They also call it a GeoServer on steroids, right? There's a whole instruction how to install a GeoServer for very heavy tasks. And tell us, what if, for example,
it really depends also what is the main point of the GeoServer. It is going to be mainly used for the rasters or for the vectors, because for some tasks, for example, for the vectors, it's mostly important to have better part in processing, but for the raster in better part in RAM for the server. So it depends also on what is the main purpose of the serving the data.
And a last question to ask you. So we also have in our project, we're developing solutions for the virtual reality and augmented reality. And does OGC has already standards for virtual reality like 3D GIS and for augmented reality? Are there already standards? Is OGC ready for that, or is it something still experimental?
I don't know, but I guess that they have something, because as soon as some new thing in web development started, OGC also started to implement the standard. So I think that there is something, but I'm not expert in that. I don't know. I guess there is something.
Okay, so thank you so much, Milan. This is super useful, and thank you so much for connecting. We're very sorry you couldn't make it to Wageningen. We're going to disconnect now. We look forward to your second talk in the conference, and thank you so much for jumping in and presenting this topic. The PDF of slides has been shared via Mattermost. So for those of you who are registered, you can access through Mattermost, you can access the slides, Milan slides. Thank you, Milan, so much. Good luck with your work. Bye-bye.
Bye-bye.
Okay, how do I stop? I need to stop the live also.